So yeah, he'll figure it out. Alright. Because this stupid thing doesn't start on for some reason. Well, I don't know. When I'm, like, look at these pens! And you can't see the pens. Yeah, I know. Well, you're part of my class. It's not your fault. I'm not trying to blame you. Like, oh man, if only you told me. Just to be clear. Just to be clear. Yo, what's up? There we go. Yesterday I played All My Exes Live in Texas for my algebra class. You get it? All my exes. Get it? It's funny. Hello everybody. Ah, this thing annoys me. How does this get over here? Ugh. There we go. Something like that. Alright, so today, do a little recap of what we did yesterday real quick. Do attendance. Give you a little problem to work on if you want to think about. This is what we did. Right, we had something that looked like, I don't know, something like this. And we said, first of all, just because there's two dots in the middle here doesn't mean we divided up the segment into 3 equal pieces, right? Doesn't mean they're equal. Just means that they're divided up. And if we were to label these like A, B, C, and D, all that we know is that B is somewhere between A and C, right? We don't know anything about where it is. It's just somewhere between them. Same thing with C being between B and D. Okay? And that B and C are somewhere between A and D. Not sure where yet, but that they are. Then we had some, like, overlap. And then we had another long segment down here. And part of the thing was they gave us this. All right, again, just doing a quick recap. I'm doing the same problem as yesterday. Which I wasn't 100% prepared to do this morning, so I do apologize for not having it in front of me. Donde está? I swear to God if I threw it out. Alright, we're going to have to recall. I believe this was 10 in length. I believe this was... Hey Blaze. Hey Joe. 14x in length, and I believe this was 19x minus 1. I'm almost 100% sure of that. And what we were doing was talking about how these segments, while we don't know where A and B, or B and C are, we do know that C and this point right here. Oh, hey, what's up? You got a new name, huh? I'm going to use J and skip H and I because, again, if you rotate them, they look the same. K and L. So we did notice that A and E and C and F are lined up, which means that A, C, and E, F are the same length. And we just started writing down some relationships, right? Trying to find, right off the bat, if they're asking, like, what's the length of AD? Right? That's a tough question. So answering some other simpler questions usually gives us some insight. So we said that EF and AC are the same length, right? Because these dots are lined up. We cool with that? Right? That's how you measure something, right? You stick a ruler up to it, and if they line up correctly, then you know it's the same length, right? So these two, whatever their measures are, have to be the same. So we wrote that. AC equals EF. You can put the line over the top of them if you want. Usually when we don't have the line, it's talking about the value of those things. Let me zoom in. If you do have the line over the top, it's specifying that these are segments, okay? Then we also said that by the same logic, isn't GJ the same as BD, right? Using that same logic, BD is the same as GJ. And we know that KL is going to be the same as AD. We also said that AB plus BC plus CD is just going to be AD, right? All those three pieces put together. And this is all just segment addition postulate. The idea that if you take a bunch of pieces of a segment and put them together, you get the whole thing. Can't prove it. It just is. Makes sense, right? And then we use this to kind of solve the problem. So because EF is the same thing as AC, that's what we said here, right? We said, well, EF is 10. And AC... well, AC is just the pieces that make it up, right? A, B, and BC. We okay with that? Again, just recapping. If it wasn't a recap, I'd have you guys, you know, figure this out on your own, more or less, but that's what we did yesterday. We don't know what AB is, but we do know that BC is 6x, which implies, this is a therefore symbol, you're going to see this a lot in that class. Therefore, we know that AB will equal 10 minus 6x, and yeah, you can use PEMDAS to figure this out, right? Subtract 6x to both sides, move it around, all that, and that's valid. There's nothing wrong with that. But if you just look at it, what does that mean, 10 minus 6x? Well, this whole piece minus this much, right, will give us what's left over, right? Does that make sense? Are you seeing that? Yeah, okay. That's all we're saying. That's going to be AB, of course. Whatever this minus this is will get us that. Doesn't matter if this is 10, that's 6, whatever, right? This minus this will always be what's left over. Same logic here. This minus this much, right, 6x, will get us what's left over here. Now, what's good about this is 14x minus 6x we can do, right? It's all x's. If I have 14 of something and I subtract 6 of that same thing, right, I have a certain amount left over. In this case, 8 x's. 6x and 8x makes 14x, right? We cool with that? 6 and 8 is really hard for me to add for some reason. I'd use 7 and 7, like I take a 1 from this and make them both 7. Or I think like 6 and 6, but then add 2 more. 12 plus 2. I don't know. Anybody else weird with 6 and 8s? I don't know why that is. It's always been strange for me. And then this one we can't do that with, right? Because we're not talking apples to apples, right? We have x's and x's, right? Here we have numbers and x's. It's like I have 10 ducks and I subtract 6 chickens. What does that mean, right? Can't do much about that. So we just put them together and say 10 ducks minus 6 chickens. That's whatever this is, right? Here to here. And then yesterday we said, well, if AD is the same as KL, we should be able to add all these up and get 19x minus 1. So we did that. We took 10 minus 6x plus 6x plus 8x, and that should equal this guy. And now we can solve that problem, right? I've got minus 6x and 6x. Let's not say we did, right? If you're taking away 6x's and adding 6x's, it's like you're adding 0, right? So let's not say we did. So we have 10 plus 8x equals 19x minus 1. Subtract the 8x, we get 11x. Add the 1, we get 11. So we end up with 11 equals 11x. Something times 11 is 11, right? The something must be 1. So all these are 1. This is 18 in length. This right here would be 4 in length. This would be 6. This would be 8, 10, 14. I don't know. Again, the key was not the answer or even the algebra. The key was being able to see the relationships and writing those down. One of the things you're going to have to get used to this year is writing down the obvious. Maybe it's helpful, maybe it's not. There is no, here's how you do this problem, here's the steps. Every problem's different, right? What's the same about them is the way you think, the concepts. Hey, I know that if I take this and subtract that, I'll get what's left over, right? Writing that down is important. That can help you get to the solution. Are we feeling okay about these ideas or no? Macy, are you okay? I know this is way too early to do math, and I went through it really fast. That was a recap. Are we okay with the recap? I'm sorry that it wasn't a full lesson, but that was yesterday. I can go back and run it over again like a dead cat. Should I? Beep, beep, beep. Yes or no? I have cats. No? Okay. So that was segment addition postulate, right? The pieces make up the whole thing. The pieces make up this whole thing, right? These two pieces make up that. So we can subtract pieces and get the leftover. As long as you understand that basic concept, I think you'll be fine. Today I want to shift gears. No, I want to talk about something different. We talked about segment addition postulate. Remember, there are very few postulates because we want to be able to prove most things, right? Postulates are a leap of faith. And the more leaps of faith we take, the more it's like, okay, are we really like thinking about this here, or are we just making stuff up, right? Unfortunately, it turns out that in mathematics, not everything can be proven. In fact, we have a theorem that says it can't, called Gödel's Incompleteness Theorem. It means that there are things in math that are true that we'll never be able to prove. We're just going to have to take a leap of faith on them. But today we're going to talk about our first theorem, something that is actually provable. And I want to see if you guys can. So first thing I want you to do, I want you to close your eyes. I want you to close your eyes, okay? Close them. You're doing great. Wonderful. Macy's like, I'm already there, man. My eyes have been closed for the last 10 minutes. Okay. Close your eyes. And I want you to imagine your X. Okay. No, not that one. Not that one. Imagine the letter X. Got it? Okay, now get your X out of your mind. Okay? Now imagine an X. Now grab the bottom two parts of the X, right? The left side and the right side, the bottom two sticks. And I want you to keep that X connected where it is, but I want you to treat the X like a pair of scissors. As you go to close the scissors, what happens to the top of the scissors? Well, of course, you're closing them so they get closer together, right? What happens to the bottom, the part that you're grabbing? It also closes, doesn't it? You know how to use a pair of scissors. If you open up the scissors at the bottom, what happens to the top? Well, of course, the top opens. Okay, now close your scissors again. Look to the left and the right of the scissors, the empty space. So between the top left and the bottom left parts of the X, and the top right and the bottom right parts of the X. As you open your scissors, what happens to that area? As you open the scissors, what happens? All right, now open your eyes. Some of y'all are like, I don't know what scissors are. I never learned how to use them. I can help. This is a scissors. I'm not sure what the plural version is of this, right? If the singular is scissors. Is one of these a scissor? Did you guys learn about that in elementary school or kindergarten? Because I never learned about that either. I feel like that would have been helpful. But anyway, here's our X, right? The top space and the bottom space. As I close the scissors to make the top smaller, notice the bottom gets smaller as well. Now view the sides. What's the relationship between the sides? Are they the same as top and bottom? Are they alternating? What's going on here? What do you notice? This seems super silly, but it's important. Yeah, go ahead. Yeah, Chase. Yeah.
Might go out, the tops from like out essentially also.
Mm-hmm. So top and bottom are connected in the same way. What about the sides? Same thing, right? Always. Always. Okay. Let's talk about angles. You guys have heard about this, right? Like 90 degrees and stuff like that. We're not talking about like the, you know, the temperature or the band that did the Mulan song at the end. Like not the new Mulan, the old Mulan. I hate how I have to say that now. You know the old Mulan? Animated, you've seen it? Yeah, the original, the OG, right? True to your heart, right? When will my reflection show who I am inside? I'll make a man out of you, right? Come on. Did they send me daughters when I asked for sons? Great, great film. So one of the bands, because you know, like in Disney movies, they always bring in like an artist to sing some of the songs, right? Like they'll have like the regular version of the film, and then at the end in the credits, will be like some, you know, like they'll bring in Jay-Z to, you know, rap something, you know, a version of it. Well, they brought in this boy band called 98 Degrees back in the 90s. You probably heard of them. They're super famous. Apparently, they're still kicking it to this day. Like they're like 40-year-old men up on stage dancing in outfits. But they did a version of it. So we're not talking about that, okay? I'm glad we've made that very clear. We're not talking about that. So get that out of your head. That's not what we were thinking. Paul, can you get that out of your head? Okay, that's not what we're thinking about. What we're thinking about is this. The relationship between two lines, right? If I draw two lines like an X, there's a certain relationship here between those two lines. And even if I draw the exact same lines again, I can have a different relationship here than I had before, right? I could even draw the exact same two lines and have it be like this. And we can tell that the relationship here, here, and here are all different relationships, right? So we need to have a name, a way of defining that different relationship to tell them apart. And we call those relationships angles. L-E-S, not E-L-S, that's angels, very different. So these are different angles. So what you're saying, Chase, when you say that the top and the bottom match, is that you're saying that the angle here is the same as the angle there. Right? So we know this is a fact. if this angle is such and such, I don't know, right? Then this angle must also be the same. Guaranteed. That's what we're observing. That is our conjecture. We're going to prove that, because again, this is a theorem. There should be a way to prove it. This angle, whatever it is going to be the same as this angle. And if you notice, this angle right here is in fact the same as that angle. Cool. This special property has kind of a crappy name. It's called the vertical angles theorem, or VAT for short. It says that whenever you have two lines and they intersect, their vertical angles are going to be the same. So vertical is up and down, right? These two will be the same. Now, I don't like this name because vertical is in the eye of the beholder. Are they vertical angles now? No, they're horizontal, aren't they? They're across from each other left to right. Does that change? Are they now no longer equal? No, that doesn't change anything. Well, wait a minute. If this is vertical now, what does that tell us about these two angles? They have to be, right? So technically, it's not just the vertical angles that are the same. It'll always be the left and right angles as well. I like calling this Scissor Theorem. There was a joke last year about how these angles are like a pair of scissors. I won't get into it. That's it. So how can we prove that this is true? Because again, it's a theorem. It shouldn't just be like, well, look, I can explain it because look at this. Well, what if these scissors are just magical and they just happen to be the same? Or what if they're not actually and they just look like they are? How can we be for sure? So first of all, we need to define how we're going to measure angles, right? 90 degrees is what we're going to call this. And if that's 90, right, that's 90. And this is 90 as well. How much must this be? 180. Double, right? Well, if that's 180, how much is this? 360 all around, 180 here, right? No, it's okay. I want you to show understanding, not just answer my questions. If I go from here to here, that's not a full circle, so it's not full 360 like this is, right? It's going to be 90 plus 90 plus 90, or 100 plus 100 plus 100 minus 30, right? Minus 10 minus 10 minus 10. So 300 minus 30, 270. Oh, yeah.
Or you can do like 9 times 3 is 27.
Yep.
0.
9 times 3 is 27, right? 9 times 10 times 3 is what we have here, right? 9 times 10 is 90, and there's 3 of them. You're doing 9 times 3 first, which is 27, and then adding that 0 on because you're multiplying by 10, right? That's where that add a 0 on comes from. We're just doing these two first and then hitting the 10. Yep. Yeah, my method was 100 times 3. We want 90 times 3, so I need to take away 10 groups of 3 to get 90 groups of 3, right? 100 groups of 3 minus 10 groups of 3 is 90 groups of 3. Right. I don't know. Up to you. So, how do we prove that the top angles and the bottom angles will always be the same? First of all, we just got to give you a generic drawing. Now, much like before when we did this, right? Remember, one of the keys was we don't want to know where B is exactly until we solved it, right? All we know is that B is somewhere between A and C. Just because it looks like it's the middle doesn't mean it is. Same thing here. I drew a random X. My X could have been tighter, it could have been wider. Doesn't matter. We want to prove it for any possible X, right? So when we talk about these angles, we're not talking about a specific measure, right? I'm not saying, okay, this one right here is 30 or whatever. We're not doing that. We're just saying here, take an X. So here's our generic X. Let's label some points so we can talk about it a little bit easier. A, B, C, D, and we'll call this point E. That's their intersection. And our job is this. We want to prove, let me write this down. Prove that angle AEB. Do you see how I did that when I talked about this angle? The middle, we call that the vertex, always goes in the middle. If I called it EBD, I'd go in EBD. Wait, what? Right? Or if I called it EBA, I'd have this angle here, right? Imagine a line going from B to A. So we always have the middle part, the vertex, in the middle of our name because it helps us figure it out, right? We can go AEB. Is there another way to label this that we could do? AEB. What else could I call this? BEA, right? It gets me the same angle. Do we agree that AEB is the same as BEA? Right? EAB would be this angle right here. So we wouldn't want to call it that. So always just make sure that the vertex of that angle that you're talking about is in the middle. Okay? Usually it takes 3 letters to be extra particular about this. Some people are like, oh, I'll just call it angle E. But there are 4 different angle E's here, right? Which one are you talking about? This one, this one, this one, or this one? So 3 letters is its full name, much like yours. So we want to prove that AEB is the same as, now, when we talk about the measure of something, we use equal signs because we're talking about numbers, right? 5 feet, 10 feet, 30 degrees. But when we're talking about ideas, that this angle is the same as another angle, we use this sign. It's an equal sign with a little tilde. You guys been in Spanish class? Right, you get the ñ, the N with the tilde. We call this congruency. So we say something is congruent if it's exactly the same. You guys heard that word before? Yeah, have you seen that at all? If you haven't, that's okay. It's just a fancy word for equal, and it has to do with figures and ideas. Numbers can be equal, but ideas are congruent. And an angle is an idea. Okay? And we want to prove that it's congruent to the bottom angle. We'll call that angle CED. You could also call it DEC. And the question is, how do we do that? How do we do that? How do you solve a problem like Maria? Yeah, what's your idea?
I'll be honest, the same answer.
Okay.
I am horrible with angles.
Horrible with angles? What do you mean?
I just don't get them.
You know what you don't get about them?
I know.
Oh, wow, that's real bad, right?
Yeah.
I don't know what I don't know. What's your experience with angles, Chase? Like, what do you remember? When you think of angles, like, what do you think of in school? Like, what was your experience with them?
Last year we had to
Okay, that's fair. I just wanted to know if you had like a particular homework assignment you might remember that was just like traumatic or something. The angles, the angles. Okay. Yeah, how do we prove something like this? Right? Doesn't it kind of feel like it just has to be, right? Look, I mean, come on. How do we prove that? That's what we're trying to prove, though. Vertical angles theorem. Yep. Yep, but how do we know vertical angles theorem is valid, right? Once we know it's valid because we've proven it, then we can use it and say, look, vertical angles theorem already says these are equal. Ain't nobody got time for that, right? But until we've proven that it works, we can't use it. So much like this problem, there's a lot going on. It doesn't seem like a lot, it's just an X, right? I mean, come on, right? But there's a lot going on here. And solving this is kind of difficult. We need to start just writing down some relationships, okay? So what do you know about angle AEB? And I'm going to use a little m. That means the measure of angle AEB. See how this is talking about the idea of the angle? This is the measure. So it's 90 degrees, 100 degrees, something like that, right? Whatever it is. If I were to add that, what's going on? Oh, yeah, I'm sorry. My black Sharpies are really crappy right now. I need to get new ones. Yeah, I figured that out yesterday, and then I was too dumb to think about it again. So what do you know about this angle here? And again, we're talking about this one, right? We cool with that? Maybe I can color code it. This angle here. And this angle here. I'm going to call that... Actually, you know what, Paul? What do you want to call this angle? How are we going to name it? We did AEB for this one. What about this one? Say it again. Say it again. D or B? I can't tell. B as in boy, D as in dog? Dog. Oh, dog. It sounds like you said no. You're just so far away, Paul. You're so far away. So D, EB, you're going to call it Deb. Good choice. Right? If we call it angle D, there's no real angle just here, right? We have to have the three-letter name to get it done. Make sense? Okay. So D, E to B is the angle. Could have called it bed as well. I don't know. 8 in the morning, I'd probably pick bed. That's just me. Do you know either of their measures? You don't, right? This is imaginary x. They could be anything. But what do we know about when you add them together? How do you know it's 180, Macy? They look like they could be right angles, but we don't know that for sure. It could be. We don't know for sure. Macy's actually right that it's 180 degrees, though. And it's not because they're both right angles. I could have drawn something like this. Ooh. Do you see how these two angles, even if one's really small and one's really big? Let me zoom in. Don't they make up a straight line? Earlier, two 90-degree angles back to back, that's a straight line. Isn't it? Oops, sorry. Two 90 degrees back to back, this guy looks so happy. Straight line. So a straight line is always 180. Isn't AED a straight line? Right? It's just an X. Right? When we drew it, we drew a straight line across. So we know that has to be 180 degrees. Okay. What about these two angles? Or to add them up. Same thing by same logic, right? It's a straight line, right? We drew it as a straight line. So this must add up to 180. So I'm going to write that down. Geraldine, what would you call this angle right here? The gray angle. What do you want to name it? CED? I'm using the same color for the same angle. And we'll call it Deb, just to be clear. So you know we're talking about the same thing. Good choice, Paul. Good choice. And we know this is 180 because it's a straight line. When something equals something, it means they're interchangeable, right? If 4 equals 2 plus 2, whenever I see a problem, I can switch out 2 plus 2 for 4, right? Whenever I want. And it should be the same. This is the same as 180. So they're interchangeable. Whenever I see a 180, I can switch it out for this. Whenever I see this, I can switch it out for 180. Uh-oh, what was that? Uh-oh, I glitched out. I am. So if this equals 180, and this equals 180, doesn't this equal that? They have to equal each other, don't they? This will be the same as that. Has to be. Because if they both equal 180, I can just write this as blah, blah, plus blah equals 180 equals this plus this, right? I can just make a long statement if I want. So what I'm going to do is I'm going to take, whenever I see a 180, I'm going to switch it out for this. I'm going to take this, and I'm going to switch it out for that. Because I know that is 180. So when I write my next statement, I'm going to write this. And sure, that equals 180, but 180 is the same as this, right? So I'm just going to write, and I'll do it in pink this time. Fair? This equals 180. 180 is the same as that, so I can switch them out, right? We call this substitution. So I switched out 180 that used to be here, right? For that. Think of a number, right? He's some measurement. Maybe it's 90 degrees, maybe it's 89 degrees, maybe it's 110. I don't know, right? And when you add something to it, it's the same as some other number plus the same number. I'm going to say that again. Do you see how these are the same? We have both green angles here. They're equal, right? Green angle is equal to itself, right? So we have something plus another number equals something, right? So these two add together to make something. These two add together to make something. Apparently that something's the same. Think of a number in your head. Now add like 5 to it. Great. Got that number? Take that same number you had originally and add something else to it. Anything other than 5. Will they ever be equal? Numbers in my head. 5 for both of these. I'm going to add 6. I get 11. 5 plus anything but 6. Will I get 11? No way. So what does that mean about these two angles? If they're both equal, right? This and this adds up to make the same thing. What does it tell you about these two angles? The pink and the gray? Chase. It says so, right? And I didn't screw up my logic, so it must be. They have to be, right? If both of these are the same, which I think we can agree they are, right? The greens, right? And after adding a number, they're still the same, then the number you added must be the same as well. Maybe you like PEMDAS better. What if I subtract this angle from both sides? That's a B, by the way. Right? Subtract it from both sides. As long as I do both sides, that's fine. The angle minus itself is 0. The angle minus itself is 0. And look what we get. We get this plus 0 equals this plus 0. In other words, we get gray must be the same as, that's what equal means, right? Pink. Gray and pink are the same. In other words, we prove vertical angles theorem. When we end a proof, normally they write like QED, which is like Latin for something. Basically, it just means proof is in the pudding. There's also another thing that mathematicians do. They do a little square to show they're done, kind of like boxing your answer. What I like to do, swag box. Done. I don't normally draw the other lines, but normally I just do this. Swag. That's just my way of doing it. You can make up your own. These must be 180 because they're a line. Well, these must be 180 as well because they're a line. If this equals 180 and that equals 180, then they equal each other. What's in common we can ignore. Turns out these are the same. How did I go about doing this? Well, you knew how to solve it to begin with. No, I didn't actually. I forgot. I was kind of nervous. Macy's like, I don't remember. It's like, I don't remember either. I don't have stuff memorized unless I do it a lot. And I only do this at the beginning of the year. How I did this is I started writing down relationships that I noticed. How would you prove that the blue angle is the same as the green angle? I want you to try that. Maybe write a post about it. How would you prove the horizontal angles are equal as well? Give me a horizontal angle theorem. Or hat. Chase, how are you feeling? Nah, I don't like angles. Yeah. We'll see if we can change that, all right? Take care. Macy, you doing all right? Okay. Hey, you two, hang in there, okay? All right, I did not take attendance. I need to double check who was here and who was not. And then we'll jump on to the next one. Also, I've got to clean those desks. Check the chat. That one? It's for the front of the class to hear you guys when you talk, so the people online can hear you. Like we had everybody here. Alright, yeah, retell me if you're here. I just opened up chat. Can you retell me if you're here? I see Olivia and I see Campbell. Let me spray it down. Chase didn't remind me to do announcements. Chase. Good morning, crusty crew. SpongeBob Bob. All right, so I see Campbell, Olivia, Jaden, Annie, Mika, and Shion. Jaden, I'm sorry, my computer yesterday was doing that thing. Well, it stopped working at around like 1, which is bad because I was supposed to meet with Cliff. And I had to shut it down. Like, I had to just completely turn it off and force it to shut down. And when I turned it back on, it took a while. But when it finally came back on, it said it was updating. So Windows is kind of screwing me over. But we will get you taken care of. I should, in theory, be available at 1:05 today. I'll send out a link for a Google Meet for everybody. All right. Let's do attendance. So again, saw Olivia, saw Campbell, saw Annie, saw Mika, and Shion. I see Theron. No Blake yet. No Marissa. No Katie yet. No Lauralee yet. No Nate in person, but everybody else is here in person. Let me know if you're here. No looking at this. No cheating. No cheating. Looking at this idea. Come on. Come on. Be sports. People in class. Normally I can like kind of view your faces and, you know, any other year. Every day, and when I do a lesson I can kind of read your minds more or less, but you also can be there to like tell me how things are going on. We don't have that because of coronavirus. Yesterday you guys were not here, obviously, and I can't read your minds through a computer. I'm not that good yet. How did yesterday go? Was everybody okay with what we did yesterday? You cool with that, more or less? Lining up the stuff, the whole thing minus a piece gives you what's left over. Let me know if we're not super cool with this, because I want to move on, but again, I can't read my class. Right, the whole thing minus this will get you that. We can write that as 10 minus 6x equals this. Yeah, okay with that? Okay, awesome. All right, I see Katie, I see Blake. All right, and Corinne is here as well. Awesome, 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 awesome. Marissa. Oh, I see Marissa. Okay. So no Lauralee, no Nate. That's what I'm saying. Okay. Rad. All right. Give me 1 second while I go close the door, and then we're gonna jump into something new today. Today is an exciting day. I've got some announcements first. Don't let me forget to do that. So if you have not met with me for the portfolio review yet, I find myself like 99% responsible, even though I'm probably only 1% responsible for that. And it's because my computer's been dumb and I haven't been able to meet with you guys, like, I don't know, today, and then a couple days ago my computer did the same dumb thing. It was the beginning of this week. So I do hold myself responsible for those things. However, I do need to see you, right? And I think we're both being honest that it's at least equal parts me and you. If you have not met with me yet, or if you met with me late, later than last Wednesday, or I guess technically last Thursday, because some of you guys signed up for Thursday time, I will need to see you for portfolio review next Wednesday on top of this week, just to make sure you're good to go and that we're keeping you on track and that you're not getting lost and behind. If you are an 8A person, which is not the people in class today, but the people online, I will see you next Wednesday for a grade. B-Day people, if you want to show up next Wednesday for a portfolio review, not for a grade, but just to get some feedback, that's more than fine. Up to you. Don't care. I can help you out. As soon as my computer is not being dumb, which again, as of today, it's not, I should be able to start getting back into comments and all that stuff and looking at what you guys are doing. And we should be able to do some portfolio reviews. I apologize that I'm behind on the comments. The reason I'm behind on the comments is because I'm spending all my time outside of school doing portfolio reviews with kids that should have been doing them last Wednesday. Which, again, no shade against those people. I know crap happens. But that puts me behind as well. So make sure we get that done as soon as possible. Today's kind of exciting because today's kind of the beginning of geometry for real. Like, this is all fine and dandy and all that, but it's a postulate, right? Segment addition postulate. It's nothing we can prove. It's just, it has to be, right? This is the whole thing, and that's a piece of it. So what's left over when we subtract will be this other piece, right? There's no way to prove it. What's up, Jace? Yeah, not this Wednesday, but the Wednesday after that. Yep. That's the plan, to give you guys more time. Eventually, we might switch back to every Wednesday type of deal, just because we won't need as much time. But right now, the people that are not meeting with me or met with me and their portfolio was just like nothing, right? I want to meet with them for a long period of time to make sure they're on track, and so we need that bigger time. So I'm dividing it up to every other week. Eventually, we might go back to every week. We'll see, which I know some of you guys are like, oh, that sucks. But like last year when we did quizzes, remember that? And it was like every other week and it wasn't every week. The quizzes got bigger, right? And obviously this year we're not doing quizzes, but you'll have to present more to me because it'll be 2 weeks worth of work, and that can be a headache to get in however much time, right? And more grades is better in theory if you're worried about grades, because if you screw one up, right, there's more of them, they're going to hurt you less. So, I don't know. We'll talk about it. But yeah, I'm excited to go on to something that we can actually prove today. Postulates are leaps of faith, right? And we don't want to have a lot of them, because if we have lots of leaps of faith, eventually we're not really proving anything, right? We're just making statements, which is fine, but it's not really that interesting. Being able to prove something is much more interesting. So we have a few postulates, right? We have to have a few, because we know that there's a theorem that says there are things in math that are true that we'll never be able to prove. There's a theorem that says that. Gödel's Incompleteness Theorem. And so what we try to do is minimize the number of leaps of faith we have to take. And one of those is segment addition postulate. Today we're going to talk about our first theorem. So what I want you to do, begin, is I want you to close your eyes. Some of you have already been doing this. Close your eyes and imagine with me a pair of scissors. Ah, are you imagining them now? Do you see them? Oh, you do. Perfect. Excellent. Your imagination is strong. So watch what happens as I open and close these scissors. Really watch, really observe. Again, it's not the scissors that matter. Think of these two scissor. Are they individually a scissor? I don't know. Think of each scissor as a line, and the point here as the point of intersection for those lines. And notice how they react. I'm not changing the size of the lines, but I'm changing how they interact. Right? The relationship between them. What do you notice as I open and close the scissors? What do you notice? Jace, what do you see? Say it again? You get like a straight line, right? Both lines on top of each other. What do you see? The angles? You're just making up words. We haven't talked about angles in here yet. Keep going, Haley. What were you saying? They changed their what?
They change each time, like however much.
Ah, so if we focus on the bottom, right? Notice as I push it closer together, what happens to the top? It gets closer together as well, right? They do follow each other, right? There's a relationship here. And math is all about relationships. Bow, chicka, wow, wow. And this is the most fundamental part of a relationship. X. Right? So, where there's an X, there's relationship. Something like that, right? So we need to describe this, because we're mathematicians. How do we describe this relationship? Jace is right. As I fold them together more and more and more, let me pull back a little bit, we end up with a straight line. And what happens to the sides? It's as open as it possibly can be, right? As I open this, what happens to the sides? They both match, right? See here and here, right? As the top and bottom get bigger, the sides get smaller. There's a fundamental relationship here, and it's a relationship we can actually prove. Let's talk about it. First of all, we need to talk about angles, because Haley mentioned angles. Chase was in my class today, and he's like, I don't like angles. I don't like them. I just don't like them. And I was like, Chase, what happened? Who hurt you? He's like, I don't want to talk about it. So I don't know what happened with you guys in angles, but it's gonna be okay. It's gonna be okay. You just gotta trust me. We're gonna face our fears today. It's like, you know, when you're afraid of snakes and they like throw you in a box of snakes. It's gonna be exactly like that. But relax. 2 lines. We're gonna talk about this relationship today. But again, angles. What's your favorite angle? You have a favorite one? Oh, Haley's so ready. What's your favorite angle? 90 degrees. Why is it your favorite angle? Why? It's easy. And it's easy about it because one side is flat and the other side goes straight up, right? Something like that. 90-degree angle. Something, Grandpa SquarePants, rock bottom, never chase after a bus, right? Haley's like, yeah, don't do that. Don't you do that. Okay. That's a 90-degree angle. Now, who decided that was 90 and not like, I don't know, 4 or something? You know why that's 90? Why they call it 90? Why do we have 12 on a clock? Why didn't we do it by 10? Any idea? What's interesting about 12? Say it again? Ah, right, but wouldn't the day be just 20 hours if we did 10? It is half of 24. Why did they choose 12 and not 10? Well, there is because there's 12, right? Which came first, the chicken or the egg? Yeah. You mean like the name? Like midnight means 12 or something like that? There's like a relationship there? Yeah, so you're thinking like the origin of the word more so. Okay. It was the day I was born? What do you mean it was the day you were born? 12? What? Oh, that's why they chose it? That makes sense. See, I didn't know that. I had heard that they chose it, and I'm probably wrong, that they chose it because it's a highly divisible number. 10 is only divisible by what? 2 and 5, and then 10 and 1, which aren't very interesting, right? It's not really division. 12 is divisible by 1, by 2, by 3, by 4, and by 6. Now, obviously, there are more divisible numbers. Like 60 is really divisible, but it's also really big. Can you imagine if there's 60 hours in the day? Right? Like, time would be very meaningless, if not already from Corona, right? It'd be even more. Like, oh, we're at 35 hours in, you know? It's like, okay, I guess that's a little more than halfway. A little too specific, right? So 12 is an easy number that's highly divisible. That's why they use it. Because you can have quarter of a day, half, 3/4. You could even go every 2 hours and get a 12th of a day, right? Or a 6th, depending if we're thinking in terms of 12 or 24. The same reason is why they chose 90 for this angle here. Because if we keep going, we put 2 90 degrees back to back, we get 180. And that is a straight line. That's how we define a straight line, 180 degrees. We cool with that? And if I go all the way around, I can fit 2 more 90s in here. How many degrees is that all the way around? 360 no scope, right? The ultimate thing to do in a video game. Snoop Dogg 420. Y'all seen that video? Jace, you're so friendly. So it's 360 all the way around, right? 360 no scope, full circle. 90, 90, 90, 90 is 360. I know that because 100 plus 100 plus 100 plus 100 is 400. Minus 10, minus 10, minus 10, minus 10. Minus 40, 360. Another way is 4 times 9 times 10 is what we're doing here, right? 4 times 90. 4 and 9 makes 36. 10 gives you 360. I don't know. Different ways to think about it. What about this? What is your conjecture based on what we talked about earlier, the scissors, right? Because the scissors is basically just an X, right? It shows you all the different ways you can make an X. Yeah, what's your conjecture? Conjecture means your guess that we're going to try and prove.
Okay. Like, top and bottom are like the same as the sides are always the same.
All right, our conjecture, Haley's conjecture is that the top and bottom are always the same and the sides are always the same. And if you look at this, which is not a proof, right? Because maybe my scissors just happen to be connected the right way, or maybe they're not really 100% the same, they're just really close, right? But it looks like our conjecture, reasonable estimation, reasonable guess, is that the top and the bottom are always the same no matter what you do. And so are the sides. Okay. How do you prove that? Or is it a postulate? We'll find out. I'm going to tell you right now you can prove it. So really we're talking about angles here, right? The top and the bottom, the relationship here, that's what an angle is, right? We know that the lines here are not changing, right? The size of the scissors doesn't change as I move it. So the relationship is obviously different here between here and here, even though they're the same lines. So it has nothing to do with length. It has to do with this weird idea of angles, right? Space in between something. So let's draw something like, I don't know, like this. That's an X. Now, we want to prove this for any possible X, not anything specific. So I'm not telling you like, okay, that's 3 inches and this is 6 inches and this is 100 degrees. No, it's a generic X. And if we can prove it for a generic X, that means it could have been any X, right? Does that make sense? We're proving it in the general case. Nothing specific about this X other than it's 2 lines intersecting. So if we're proving it for something as simple as, hey, it's just 2 lines intersecting, then we've proven it for any 2 lines that intersect. If it's 2 lines intersect and it's 3 over here and 6 over there, well, then we've proven it for something that has 3 there and 6 there, which is not what we're interested in doing, right? We're interested in proving it for all possible intersections. So we're going to keep it as basic as possible. Let this be an intersection of 2 lines. So I'm going to write that. Let's call this line A, B, C. Let ABC be a line segment. Cool. We're setting up the problem. Yeah. Yeah, right? In order to prove what we want to prove, right? We're trying to prove that given 2 line segments that intersect at some point, the angles in the top and the angles in the side will be the same, right? So we're setting up the illusion. We're using our imagination. Let ABC be a line segment. That's what this means, right? And we're also going to let DBE be a line segment. Could I have called that line segment EBD? Sure, right? Order matters only so that we know that B is between D and E, right? And B is between A and C. If I were to just give you this, no picture, what do you know? B's in the middle. They intersect at B. See how they share the letter? That means they must intersect there. Has to be, right? So all we've done is said, hey, I'm giving you 2 line segments and they intersect at B. Where's B? I don't know. Don't care. Doesn't matter. How long are the line segments? Don't know. Don't care. Doesn't matter. All we're saying is that 2 line segments, they intersect at B. Cool? All right. And we want to prove your conjecture. What was your conjecture? Yeah, yours.
Oh, so that's the top and the bottom.
The angles, right? Is kind of what we're talking about, this idea of angles, right? That we defined earlier, right? And again, oh, did I make it clear? 360 is a really divisible number. It's divisible by 2, divisible by 3, divisible by 4, divisible by 6, divisible by 12. On and on and on and on and on. Okay? That's why they use 360. It's highly divisible. You get nice numbers. You don't get fractions when you divide it up. Okay? At least not very often. Divisible by 5. It's divisible by a lot. Okay, so we're going to prove that this angle here, and let's give it a name and a color, because I like colors. What do you want to call that angle? How are we going to identify it? Don't call it the pink angle, because pretend we're in black and white for a second. We need a good way to identify it. What? Ah, the black angle. But what's that going to be different if I'm in black and white than this angle, right? They all look black to me. Racist. All right, so how are we going to name it? Well, we gave our segments a name, A, B, C. Clearly, we know what segment we're talking about, right? Could have been CBA, same segment, right? Angle F? We could do that. Or angle 1, right? Is there a way we can label it without having to add more on here? Because this is going to get a lot messier. What? A shape? What do you mean?
Like the straw shape. Like,
Oh, sure. You could be like angle square or something. Or interesting. I like this. But I'd have to draw something. Is there a way where I don't have to draw or write anything more and I can still know what angle we're talking about? How do I tell that angle apart from this angle or that angle or that angle? Without looking at the diagram. What do you mean? No, so I have to draw something different. Sarah? DBC for this guy? DBC, when you say angle DBC, is that what you said?
yeah.
Whoever invented the beginning of the alphabet's an idiot. A, good job. Fantastic. That was good. B, okay, sure, why not? C, wait a minute. D, E, G.
F is after E.
Well, I'm talking about, you know, the connection between B, C, D, and G, and E, and Z, and T, and V, and P. They all sound the same. And if I can't see your mouth, it's kind of hard to tell. Idiot. God, who did that?
What if I did that?
Then even dumber. No, actually, I don't blame you. I blame society. Who put this kid in charge, right? It's really our fault if it was you that did it. So DBC, clearly, if I say DBC, do you all agree that we're talking about this angle? Couldn't be this one, right? Because where's the D's over here, right? So let's call this angle, what are we going to call the pink angle? ABE makes sense to me. What if I called it EBA? Would that work? EBA? Yeah, it works. What about BEA? BEA. It's like we had extended a line here and we're talking about this angle, right? Right? B has to be in the middle. I think that's a good rule. We call that the vertex, the middle, where they join, right? So angle ABE, we're going to prove that that is congruent to this other angle. And we'll use colors just to make it easy. We're going to prove that it's the same as angle. What angle is we going to call this, Sarah? DBC. CBD would have also worked. That's legal in this state, right? Good. And we're going to prove that they're the same. In other words, equal sign, right? Now, it turns out, this is kind of silly. Sometimes you're talking about ideas like an angle or a line segment, right? These are ideas, they're concepts, they're figures. You agree? And sometimes you're talking about how much they measure. Like when you use a number, they're 90 degrees, they're 10 feet long, right? Numbers can be equal, but ideas, figures, can't be equal. We use a different sign for that. We call it congruent. It's equal with a tilde. It's fancy. You know, in your Spanish class, and you have like the N with the tilde, Enya, right? Anybody like Enya, the band? I'll have to play some of their music. It's meme-tastic. Okay, so we're going to prove that these are the same. That's what that means. The symbol we call congruent. Okay, congruency. It's just a term you might have heard before, maybe, and if you haven't, it just means equal. Ideas are the same, right? Figures are the same. So we're going to prove that top and bottom is the same. Do we also need to prove these guys? Because that was part of your conjecture. Do we need to prove top and bottom and left and right? We'll do one at a time. But if you want to go back and prove left and right, you can go ahead and do it. Let's start with top and bottom. So this is a hard problem, much like what we did the other day with all the lines, right? It was like, figure out how long AD is. It's like, oh my God, there's numbers everywhere. Don't worry about that. There's no, here, do these steps and you get the problem right. That's not going to happen in here. There's too many different problems. The only thing that's going to be the same is let's write down relationships and see how we can mess with them, right? So let's write down some relationships. What do you know about these angles that we have here? We have 4 different angles. Really, we have more than that, right? Technically, this could be an angle, right? And then all the way around could be an angle. But we have 4 main angles. What do you know about those angles?
You know that pink and blue, that we,
Say it again?
you know that we,
Yeah, they both share that vertex. That's true. What else do you know? The whole thing is 360. Whoa, how do we know that? Okay, so I'll write that down. So we know that the pink angle, I'm going to use pink, plus, right, because we're putting them together. Ooh, this is like an angle addition postulate. You're allowed to put all the angles together, right? The pieces of the angles, kind of like segment addition postulate. Okay, sure, you can put angles together. Let's do that. Let's have this angle be green. And then we add blue. And then, Ethan, what color do you want the last one to be? Black? Okay. We know that equals 360, right? Because that's what we define 360 degrees to be, right? All the way around. Now, do we know that all these are 90? No, we don't. It could be like 100, and this is over here is 20, and so on and so forth, right? But at the end of the day, we know they equal 360. They have to. It goes all the way around. 360 no scope. When I used to sit here, I could spin in my chair. I can't do that now. Sorry. I just have to imagine. What else do we know? What other things? Yeah.
you know that whatever it is, you have to black.
How do we know that? Because scissors? That's what we're trying to prove. We don't know it yet. Once we've proven it, then we know it for sure. Haley, what's your idea? Yep, Jace mentioned that earlier. B's in the middle for all the angles. They all share that vertex. That's true. You want to do something with that? You guys, you keep bringing it. You both brought it up. You want to do something with that, or you're just giving me observations? I didn't know if you saw like a next step or something. Okay, you're just stating what you got. That's fine. That's good. I don't want to discourage that. What other relationships do you notice? How did we make this drawing? They're 2 lines. So we know that for sure. What does that mean? If they're both lines, what does that tell you about some of these angles? So the whole thing's 360, right? Circle. Wouldn't you agree that this is half the circle? Has to be, right? Has to be half. This is a straight line. What does that tell us about those 2 angles? Haley. They're parallel? What do you mean by parallel? Are you talking about this idea? Which angles? Angle ABE, is that what we're talking about? Okay. Kind of like the same height. Are you saying these 2 angles would be the same? Is that what you're saying? That's what you're saying, or yes? Or no?
I don't know.
Okay, that's okay. Because again, that's what we're trying to prove. You're going to feel like that a lot in here. You're like, it is. It is, especially at the beginning, because we're doing kind of obvious things, right? Sarah, you have something to say? No? What do you know about pink and green's relationship?
They equal 180.
How do you know that?
Because A,
Right? Isn't a straight line just 90 and 90 together, 180? Doesn't matter how many cuts I have in it or where I cut it, that's still a straight line from here to here, right? So because this is a line, ABC is a line, we know that this has to add to 180. Do I know that they're both 90? No. It could be like 180. It could be 150 and 30. I don't know. I don't care. But I know that they add up to 180. So we're going to say pink and green makes 180. In other words, they're supplementary. Have you guys heard that? Supplementary complementary angles. If you haven't, that's okay. They add up to 180 because they make a straight line. Okay. What other angles add to 180? Blue and black also adds to 180. What else adds to 180? Pink and black. Right, it's all by the same logic. It's because pink and black makes a line, right? Well, we want to know about pink and blue. So far we have pink, and we have a blue, and we have pink. What else we got? Say it again? Green, so something about green. Green and what makes 180? Green and blue, okay. That's a lot of information. That's okay. I think we got all our pairs, right? Green and blue, black and blue, black and pink, pink and green. Now we care about these two, right? That's what we're trying to prove. Okay. Hear me out. I was able to write this sentence because if this equals 180 and this equals 180, then don't these equal each other? Right? They're all equal, right? They're all the same. Same thing here. I could have set them all equal. I just ran out of room. Well, isn't it true that if pink and green equals 180, then green and blue equal 180? Doesn't that mean pink and green equals green and blue? This should equal that. And any other combination, right? I'm choosing these two because they both have a blue and a pink in them, and I want that. Also, they share a green. I'm going to show you why I chose that, okay? This is a pro gamer move that I'm about to do. So, therefore symbol, you're going to see that a lot. Therefore, we know that this is true. Are we cool with that? Right? This equals 180, that equals 180, then they must equal each other, right? If 4 equals 2 plus 2, and 4 also equals 3 plus 1, then 3 plus 1 and 2 plus 2 must be equal, right? Imagine you have some value, like 90 degrees. And then after you get done adding a value, it's the same as after you got done adding this value. What does that tell you about blue and pink? Maybe you like PEMDAS better. Anything minus itself is what? Anything minus itself is 0. So we get pink. Anything minus itself is? So we get blue. Pink and blue are the same. These two add to 180. These two add to 180. If green and pink makes 180, and green and blue makes 180, then pink and blue must be the same number, right? Pink plus green is 180. Blue plus green is 180. So think of a number and add another number to it. You get 180. Great, awesome. Now take that first number you had and add another number to it. It also gets 180. Wait a minute. There's only one way to make 180, right? If I tell you this is 100, then this guy has to be 80. And if I tell you this is still 100, then this guy has to be 80 as well, right? What if I tell you this guy is 45? Well, this has to be 135. Well, if he's 45, then he has to be 135, right? You see how it's connected? There's a relationship there. Whatever this guy is, he sets the other two. Whatever this guy is, he determines what the other two are. This is a proof. Turns out we didn't really need this guy. It's true, but we didn't need it. We didn't really need this guy. It's true, but we didn't need it. All we needed was this. And where they overlapped, we could subtract, right? And get what we wanted. There is no formula or steps to solve stuff like this, improve something. There's lots of ways to do it. And sometimes you get extra information on the way. But the logic, that's what's going to be the same throughout the rest of this year. That's the stuff we got to get used to. It's how you think and how you see the problem that you got to get trained in, right? It's not the, hey, follow the steps, remember the 5 rules, PEMDAS, right? No, it's not that. That's why geometry is so different than most of the rest of math, because unfortunately, we've taught you math in a way that's procedural. Follow the steps, get your answer, move on. Don't think about what it means. Don't think about why it's true. And then you get to here, and you're like, oh my God, this isn't math, when in reality, the stuff you were doing before wasn't. It was calculation, which is part of math, but a very small part of it. Calculators are good at calculating. Mathematicians are good at math. We're going to focus on math now. How do you feel about this? Since these are straight lines, we know that this is 180, and we know that this is 180. If pink and green makes 180, and blue and green makes 180, then pink and blue must be the same. What are they? I have no idea. Maybe they're both 30, maybe they're both 10, maybe they're both 90. I don't know. But they have to be the same. No, that's less. We call this vertical angles theorem, or VAT for short. And I don't really like the name. Call it Scissor Theorem a lot. VAT, vertical angles theorem. We've just proven it. Later on, you'll be able to say, look, vertical angles theorem, these are the same, right? But for now, I'm going to want you to prove that vertical angles is true. Write a post about it. If you understand it, write about why it has to be. Show your logic. Question, we proved pink and blue are the same. How would we prove green and black are the same? Same thing. How do you know it's the same thing? Haley, walk me through it. Jace, you're right, but walk me through it, Haley. I want you to explain that thoroughly, convince me. And if you're not sure about whether you've convinced me enough, that's okay. That's what the comments are for. I want you to work on that argument, okay? I'll see you guys later. Take care. When you see Chase in the hallway, go, angles! See if he gets scared. Bye. Today is a good day. Mr. Barkley? Good to see you. Oh, just teaching. Excellent. Wonderful. You too. Guys keep chasing it. What's up? No. Oh, what are you doing, man? Sharpening knife. That's not how you do it, right? It was locked. It was worse when they were doing this. Okay, it's not in here. I was bleeding all over the dock. Today's an exciting day. We're doing geometry for real today. We're not just taking leaps of faith. We're actually going to prove something today. This is what happened. They were putting a numbing straps in, and I just started squirting blood and couldn't feel my hand.
That's something bright.
Those are in the chemistry project.
What is bright?
The chemistry video.
Yeah, I got to do some announcements before we begin,
I
but then we'll
sliced
get
my
into it
hand
proper.
open. I was in the hospital for a little while.
That's how you slice your hand open?
Yeah, doing a chemistry video. Sharpening a knife like.
Wait, in chemistry?
Yeah.
Oh, it wasn't like at home you were just messing
No,
around?
we were doing a video.
And you were sharpening a knife in chemistry?
Yes. No, so we cut a bottle for chemistry. It's for a video. I had to cut a bottle. And
Oh, right.
So I'm
okay.
sharpening it, and then I bled all
I've seen
over.
some of those videos. You guys seen Diana and Taylor's, right? And then I also saw Natalie and Lexi's.
Well, I think we got my
And
cutting my
Marissa
hand. I think I got cutting my hand open on video, so I'm about to post it. To edit the video. Then we have Andrew. I have Andrew in slow-mo missing your glass bottle because we were playing baseball with glass.
Good morning. All right, so it looks like no Cliff today. Or actually, I don't see Cliff yet, is what I'm going to say. Yeah, let me know if you're here, guys. Steven, let me know if you're here. We're doing geometry for real today. It's exciting. Last year, I played it like super carefully. I didn't want to get into geometry too quickly. And this year, we're getting into where I was in the beginning of quarter 2 right now. I took it slow. I wasn't sure how crazy we'd go, and then it worked really well, so we're going full steam ahead. Today is an exciting day. Hey, Cliff.
Mine's right next to me.
Yes, it is. And it's because when it's close to me, it picks up an echo. I also turn those around because they're directional, those two guys. And so in theory, if I'm talking into the back of it, it won't pick me up as much. Which means I can turn them up louder and we can actually hear you guys. Or the people at home can. Rowan is here. Steven's here. Wonderful. Skylar's here. Yeah, stick around today, guys. Today is an exciting day. Don't see Lindsay or Geneva yet. Don't see... Oh, I do see Maddie. And then Carter, I see you. So Skylar, Geneva, Lindsay. I'm going to use the restroom real quick because we have people file in. I think the rest of the teacher's bathroom is available right now. I want to throw this up on the board. Throw it up. Are we cool with this? I want you guys to decide if we're cool with this idea. By the way, that symbol right there is a therefore. You're going to see that a lot in here. The 3 dots for the triangle. Are we cool with what we did yesterday in the idea here? The idea of, hey, here's 10. Since this is a piece of that 10, because they're lined up, right? I can do 10 minus 6x, and that's what's left over, right? And literally, when we say that's what's left over, we can call it 10 minus 6x. How much is left over? Well, whatever 10 minus 6x is. That's what this is. You dig? Are we cool with this concept? I'll be back in just a second. Sorry, I heard myself on the way over there. Never mind, someone's still in there. Darn. Never mind. I'll just hold it. Why'd you go to the bathroom before class, Mr. Max? Shut up, kids. All right, so we digging this? Are we cool with this? Because I can't see your faces when I do this online. I just want to make sure we're all right. Should I recap it? Yes, recap it? Okay. So again, if you wanted to know how long AD is, first of all, it's a tough question without this filled in, right? The stuff I wrote in. The first thing you want to do is not answer the original problem, but trying to find other smaller questions to answer. Like, well, AD would be the same as KL, right? They're the same. I think that's clear. They line up. I know AC and EF are the same. I know BD and J are the same. Again, relationships. I know that if I add these 3 pieces together, whatever they are, it's going to be the same as KL, right? I do not know anything about B's location other than it's between A and C. I don't know if it cuts it in half. I don't know any of that, okay? Don't assume that. All I know is it's between A and C somewhere. All I know is C is between B and D somewhere. And that C lines up with F and B lines up with G. A lines up with E, D lines up with J, blah, 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 right? But don't assume that this is each a third of the line, okay? That's not how that works. Can't assume it unless we're told it. And so what we did is we said, look, 10 minus 6x is how much this will be, right? This minus this piece will get us that piece. This whole thing lines up here. So if we take away this much from it, what's left over will be here. And this is kind of nice. 14x minus 6x is 8x. Right, we're talking x's and x's here. We can subtract them. 14 chickens minus 6 chickens is 8 chickens. Here we had 10 chickens minus 6 ducks is, well, I don't know. It's whatever that is, right? So I just wrote it like that. Couldn't put them together. It's not 4 or 4x. Then we said all these added up should equal 19x minus 1. I did that. Since we have a 6x here and then a minus 6x, isn't that just 10? Oh, yeah, it is. We actually could have skipped a step. We could have just done, hey, look, 10 plus 8x should be this. And that's what we got. Did math. We get x is 1. Trust me on the math part, okay? Yesterday, we actually didn't talk about this idea. I glossed over it. What happened is we wrote it all out, this plus this plus this, and we noticed these two cancel more or less, right? Subtracting 6x and adding 6x. Let's not and say we did. right? Get out your calculator, add 6, now subtract 6. Right. Let's not and say we did. Save everybody some time and battery, right? So we said it was just 10, which really just means we took 10 and this and added them together and got this guy, right? We, oh yeah, sorry, Adam.
Adam!
There we go. Hi, Lindsay. Hi, Geneva. And so we set up the equation and solved, and we got 1 for x. Trust me on that, okay? How do we feel about lining things up and noticing that this minus this much would get us that? We cool with that? Max, you okay with that idea? Same logic over here, right? These two pieces make up 14x, so if I take one piece away, what's left over will be this. 14x minus 6x is 8x. And that these line up, so all of that should add up to this. I don't know, segment addition postulate, right? We talked about how you can't prove that you can take the pieces and add them up and get the whole thing. And that'll always work. But it just seems so obvious and like so essential to math that we allow it to be a leap of faith. Now, we don't like having lots of leaps of faith because eventually it's like, okay, well, you haven't proven anything, you're just making crap up, right? But we do know mathematically that there's a theorem that says there are some things that are proven to be true, or sorry, let me rephrase that. There are some things that are true in mathematics that we'll never be able to prove. There's some things we just have to take a leap of faith on. So we try to minimize that as much as possible. Segment addition postulate's one of them, okay? You're allowed to take the pieces and add them up. But today we're actually going to prove something. We're going to prove a theorem. Theorems are proven, postulates are leaps of faith. We're going to start with imagination. I want you to imagine as best you can a pair of scissors. Close your eyes. Imagine the pair of scissors. Do you see the pair of scissors? Do you see them in your mind? Do you see them? Are they, the handles are black and the scissor part, the cutty part is metal? Do you see it in your mind? Can you see it? Oh my God, you can see it. You've imagined it. You've done it. Okay, perfect. Okay. So really why we're thinking of scissors is because we're thinking of two lines that intersect. And I think scissors are a good example of that. Where they intersect doesn't matter. It's just that they do. And notice, as I open and close the scissors, the size of the scissors does not change despite them being imaginary. But you can tell that there's something different about this than this, right? There's kind of a different relationship going on there. What do you notice about the relationships here? What do you see? What do you see? Go for it. Don't be afraid. As I open and close the scissors, what do you notice? I'll pull back a little bit. There's some kind of relationship going on here, and as mathematicians, we describe relationships. That's what we do. How would you describe what's going on here? You're covering your eyes because of the sun. Sorry about that. What do you notice? Imagine that these two scissor, is it a scissor? Angle! We haven't talked about angles in here. What do you mean? That's okay, keep going.
The lines are turning.
The lines are turning? What do you mean by turning?
They're going from like here and they're going like this.
So like, wait, what?
Like if I have, imagine I'm holding something and it's like this.
Oh, like a wheel around it, and like if you just focus on the one scissor, is scissor the singular of scissors, like the piece of it? I don't know.
I would just call it a blade.
Right? And if I hold one still, it kind of like rotates and it forms a circle. Ooh, that's interesting. That's true. So this guy right here, can this move all around the circle, this little black part?
No.
It can't. How far can it move around the circle? About half, right? 50%, about half. That's interesting. Okay, awesome. And this guy does the other half? Interesting. Okay. What else do you notice? Josh, you were on to something about angles. What do you notice about the angles that you're seeing here? We'll talk about what angle means in a second.
Straight up and down. This way.
People are gonna ask me like, you know, Mr. Bartos is always like, "How are you doing today? How's your day?" I'm just gonna, bah. All right. There's something about this. Bottom. What do you notice about the top and the bottom and the sides and all that? What relationships do you see?
I don't know. They're getting closer
Straight
to
up and
farther
down.
apart.
They're straight up and down like this.
They're parallel.
So eventually they end up being the same line, right?
Yeah. Oh god.
And they can be kind of the same line if I like try and push down really hard. No, I don't want to do that. I'll end up like Josh. Right? Josh, you walked that road so I wouldn't have to. Those of you at home, Josh sliced his finger open the other day, sharpening a knife for a chemistry video.
That was for the chemistry?
Yeah, I got it out.
You're gonna use it.
Safety. Oh man, that's actually kind of funny. That'd be something I would do as a kid.
At least you show him
Yeah.
what not to do.
Yeah, what not to do in the chem lab.
Yeah, slice your hand open.
It's weird, because I had to, like, I don't know what it was, but it was just, like, chilling at home, right? And I just had this, like, it was like, not, I don't want to say it's a vision, it's not like some
Deja vu.
anxiety. Like, I just had this idea that somehow I'd have to call my dad because I got a piece of glass stuck in my hand.
Wait, this was just like something you thought about and then you
Yeah.
like started panicking?
Yeah.
Okay,
I was in the
maybe we
hospital.
shouldn't imagine things from
I was
now
in the
on.
hospital for like.
No imagination. No imagination allowed in here anymore. That's a little too real.
I forgot to take my meds, can you tell?
Yikes.
I got a video of me getting this. My hand.
Oh my god. Third hour has a certain vibe to it. It just has a very certain vibe. It really does. It's very different than all the rest of my hours.
I don't want to get my phone back. I'll have to show you the video of my mom, like, picture of my mom. I showed you it, right?
Petting me like a dog.
I remember when I used to teach kindergarten and I'd be like, okay, what do you guys think? And they'd raise their hands and be like, I went to Disney World yesterday. Let me tell you about my dog. And it's like, no one asked. I don't have to deal with that in high school, though. That's good.
Oh,
I know. Lily's
Speaking
even
of
joining in.
scars on hands,
Oh my god. What do you notice about the top and the bottom and the sides? What do you see?
That finger knuckle.
This is show and tell all over
My
again.
knuckles because I fell off a zip line.
I had a corner.
Anyway, back to scissors.
Well, no. It's not that we're not supposed to talk about this stuff. It's that it started off really entertaining, and then after a while, Adam's just like, I got a scar on my finger. It's no story. I just want to participate. I want to be part of the group. It's like, Adam, no. You'll never be one of us. All right.
Anyway, back.
Cool kids only.
There's two circles at the bottom of the scissors.
What do you mean 2 circles at the bottom? Oh, wait, like this? Okay, but we're imagining lines here. I mean, if you want me to use pens, I'll use pens, right? Right?
Now the cap circle.
Josh, I'm gonna stab you.
No, it's okay. No stabbing.
He already got stabbed.
That's right. Josh knows just what to do. Let's talk about an X, okay? Not your X, okay, this X. We're gonna talk about that. So get them out of your head. Angle gets wider.
We don't talk about angles here.
Yeah, no, it's okay. So we'll talk about what an angle means in a second, but I think what he's talking about is this, right? This bottom gets wider. What happens to the top when the bottom gets wider?
Top gets wider.
Okay, what happens to the sides as the bottom gets wider?
Yeah, smaller.
Sides get smaller. There's a relationship going on here between them. Now, this space in between these lines, we're not measuring in inches or feet or anything like that. What we're doing is we're measuring it in angles because imagine bigger scissors held the exact same way. If we measured it in inches, the length between here and here would be different, right? Even though we're talking about the same relationship, right? We can imagine that bigger scissors held just like this should be equivalent to smaller scissors in some way, right? There's some way similar. So what we do is we invent this concept of angles. Good job, Cliff. Good job. All right. Let's talk about angles. Let's talk about angles. What's your favorite angle?
90.
Acute. You wish. 90. All right. And we like 90. It's our favorite because it's easy, right? It's straight across and up. 90-degree angle. Now, why do they call it 90 and not like 3 or 4? Like, who came up with that as straight? Like, why not 100?
Because of full angle.
Well, it could be, right? We just make it up.
I know.
Yeah.
Because a straight line is 180 degrees, and 90 is half that.
But wouldn't it be nicer if a straight line was like 200?
Yeah.
Or maybe it was like 100 all the way across and 50 was halfway. Why'd they choose 90 and 180?
Math.
You didn't know how to count to 200.
Why is a clock on 12?
Because that's how time works.
Well, it doesn't have to be.
Do it.
No, 24 hours.
That's how they do
Yeah,
it.
we could do it 24 on the clock. We could do, we could even have the day be 20 hours, right? Just make an hour longer than it is now, right? Why did they choose 12? Why did they choose 24?
That's how, like, they.
Because why not? Yeah.
That's how they count in England.
But you might need a reason why, because you got to get everybody to agree to use this, right? How do you convince people that 12 is the best way to do it? Or that 90 is the best way for this?
It's like.
Yeah?
Busted. That's why not.
Again, if you want to convince people, because why not, it's not a very good reason. It's an acceptable reason, but it's probably not a very good one to convince the rest of the
It was
world.
back in like ancient Greece, you could say that like the gods say it was
The
like
gods
this, so.
determined 12 to be the perfect number. So it turns
That was
out,
then, this is now.
as far as I'm aware, it could be the Greeks, could be gods. I don't know. I'm just some guy making stuff up. I could be wrong. But from my understanding, the reason they chose 12 is because 12 is highly divisible, right? 10 is only divisible by what? Two numbers? 2 and 5, right? I mean, 10 and 1 technically, but that's not that interesting, right? Everything's divisible by itself. Everything's divisible by 1. We can ignore those, right? Any number you propose is going to have that, right? So 2 divisors for 10, but 12, how many divisors did it have? 2, 3, 4, 6. Much more divisible. What about this? Because 90 is not the full story, right? Rowan's correct that if we go another 90, we make a straight line, and that's 180, right? And if we go all the way around, that's 4 90s, correct?
Yeah.
That's 360 no scope. Snoop Dogg, right? 360. Now, why did they choose 360? Because 360 is highly divisible. It's divisible by 2, by 3, by 4, by 5, by 6, by 8, by 9, by 10, by 12. Need I go on? It's very divisible. It's a very nice number. So if you want to do a quarter turn, oh great, no big deal, do 90. You want to do an eighth of a turn? Great, do 45. You want to do a tenth of a turn? Great, 36 degrees. You want to do a 12th of a turn? Awesome, we can do that too, 30 degrees. You see how it's really divisible and you end up with not a lot of fractions? That's why they chose it. They knew you were going to doing parts of a turn, so make a number that's easy to divide. 10 kind of sucks, right? I want to do a eighth of a turn for 10. Oh, no thank you. No thank you. Wouldn't want to do that, right? An eighth of a turn's not that crazy, right? Here's half a turn. Here's quarter of a turn. An eighth of a turn is just here, right? That shouldn't be too much to ask. 45, right? For 360 as a base, works out really nicely. For 100 or 200 as a base, oh man, right? No thank you. I'd rather not. I guess you could do 25 for each of these. 100 wouldn't be that bad. But after that, 12 and a half for a 16th of a turn. So 360 is highly divisible. So that's why they mean by angles, and that's what they have by 360, meaning 360 degrees. They chose that because it's highly divisible, and angles is just how much we're turning, right? And there's this kind of relationship between here and here that's a turn, right? How much of that is of the full circle? So you guys mentioned earlier that this line right here, when it moves, it takes up half a circle, right? If the other one stays still, this forms half a circle. Well, that's because it's a straight line. It's able to move 180 degrees. Same thing with this guy over here. Okay. Cliff made a conjecture. And a conjecture is just an educated guess. He's like, look, this is something that I think is true, and now I'm going to try and prove it. That's what a conjecture is, okay? It's not proven yet, but we're going to attempt to. So Cliff said, if I have two lines, right, just randomly like this, doesn't matter how they intersect as long as they do. Let's call the first line A, B, C. So we're going to say imagine or let ABC be a line. That's how we say that. And now we're going to say the other line, let's call it something else. Let's do DBE. Now notice that DBE and ABC both have a B in them. There's a B? Yes. It's where they intersect. You can tell without even looking at the drawing that they intersect, can't you? They both share that point. So they must intersect there. So let two lines intersect. Did I say anything special about those lines? No, I didn't tell you. Well, it's 3 inches on this side and it's 6 on that. No, no, no. We want to prove this for any possible X, okay? Not just a specific one. So we're keeping it as generic as possible. Two lines intersect. Cliff says this angle here should be the same as this angle here. as the bottom gets wider, the top gets wider, and they match always. Now, we can't prove this with a pair of scissors, because maybe my scissors are just perfectly aligned where the top and the bottom always match up, or maybe it's just really close, but not quite. We have to prove it for a generic pair of scissors. Right, two lines intersecting. So how do we prove those two are the same? Well, much like this problem, in order to get the answer we want, there's a lot of other relationships we have to figure out first. So let's not try and prove that those are the same right off the bat. Let's try to find other relationships. What do you notice about other angles in this diagram? Let's label them with some colors. We have a blue angle, and we have a red angle, along with a pink and green. What do you know about these angles? What relationships do you notice? Oh, go ahead, Ron.
That's okay. The blue and the red probably, like, they look like they would be equal, and then all of them together.
Oh, gotcha. Okay. So I forgot to write this down, but Cliff, what he wanted to prove, or at least his conjecture, the thing that we're trying to prove, is that the top and the bottom are the same, right? So we can say green is the same as pink. We use this symbol for the same as, because we're not talking about a number. Numbers are equal. We're talking about figures, ideas. So we use this symbol. It's called congruent. And really, if we want to write it officially, we would do it differently. Because green angle and pink angle is fine, but if we don't have color, how would we call them by their names? Green angle. How would we identify which angle we're talking about if we didn't have the color? ABE. That works. Right? If I say ABE, can't you follow that path and see exactly what I'm talking about? Yeah. What about EBA? Does that also work? Yeah. What about BEA? BEA? Nope. That'd be like this angle, an imaginary one, right? So it turns out the B always has to be in the middle, because it's the vertex. It's where they come together. So whenever you talk about an angle, always make sure you call it by its middle, in the middle, okay? So EBA is fine, ABE is fine, B anywhere other than the middle, not so much. Maybe you want to call it angle B, but here's the problem. I've got a lot of angle B's, right? Use the three-letter name. Makes it easy. What are we going to call the pink angle then? DBC. Do you want to call it DBC or CBD? I think that's a good choice. We did it, boys. So these two angles are the same. That's what we're going to prove. We haven't proven it yet, but that's Cliff's conjecture, that the top and the bottom always have to be the same. They're related. That's what he saw. So now we're going to prove that that's true. Maybe it's a postulate and we can't prove it, but I'm going to say we can. Okay? So we're going to try to. So how do you solve a problem like Maria? How do you prove that that is always true for any x? Well, first we say, let there be an x, right? Two lines. They intersect at some point. Where? I don't know. B. Where's B? I don't know. Well, it doesn't have to be. We didn't specify that, did we? If we did specify it, all we'd be proving is that this is true if it's right in the middle.
Where the points cross.
Right? Wherever they cross is where they cross. If we say specifically in the middle, then we've only proven it for a special kind of x, right? The x that's perfectly in the middle. We're going to prove it for any x. So what other relationships do you notice? Rowan said blue and red are going to be the same, and pink and green. That's another conjecture, right? We'll just focus on pink and green for now. Rowan also said earlier that this is true.
Oh, didn't see that.
What do you notice? What does that mean about our diagram?
ABE and EBC probably equal.
ABE and EBC equal 180. How do you know that's true?
It's a straight line.
They make a straight line, don't they? So we had segment addition postulate, where you can take the pieces and add them together for the segments, right? Lines. There's also angle addition postulate. The pieces of the big angle, the straight angle, you can add them together. So we know, because this is a straight line, that green and red, whatever they are, I don't know what they are, but they have to add up to 180, right? Could be like 80 and 100, could be 30 and 150. I have no idea. It could be 90 and 90, right? We didn't specify. Just some random x. But I know they have to add up to 180. Is everybody okay with that logic? I could write ABE and CBE, but I'm not going to save time. I'm going to use green angle and red angle. But Rowan did an excellent job of using their three-letter names. So we know this is 180. Awesome. So we have something about green, right? What do you notice about the pink angle? What kind of relationship does it have? Right, green and red go together to make 180. What about pink? We don't have anything about pink yet. Remember, this is what we're trying to prove. This is what we're working on. Pink and blue, what about them? They must add up to 180. Why? By the same logic, right? They make up a line. So pink and blue add up to 180.
To pink and red.
So to pink and red. Again, you're going to notice you're going to get a lot of information when you start working on these. Some it's going to be useful, some isn't. You said pink and red. All right. What else? Whoops. Wrong red. And green and blue. Those are all 4 combos, right? So pink and red and green and blue. Okay. Cool. Again, there's no steps to follow here. It's not do steps 1 through 5, and as long as you don't make a mistake, you get it right. Every proof, there's a different way to do it. Lots of different ways to see it. So just start writing down information that's true. Make sure it's true. Justify why, right? Well, because it's a straight line, blah, 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 right? And see what you can do with that. Now, true or false? If A equals B and C equals B, then A equals C. I'll say that again. If something A equals B, and we know something else equals B, doesn't A and C, aren't they going to be equal as well? Right? In other words, if this equals 180 and this equals 180, doesn't that mean this and this are equal? Yeah. They have to be the same, right? I want to pick one with green and one with pink in it. Let's do this one for green. So green and red equals 180, right? We need one with pink in it that equals 180. We have a choice. We can do pink and blue or the pink and the red. If we have stuff in common, that's usually better. So let's do pink and red. That's just a general tip. So this and this must be equal. These two right here. This guy and this guy must be equal because they equal 180. Could I match up others? Sure, why not? But we're going to use this. Now check this out. We want to prove that pink and green are equal. We've already got them in an equation. We're close, right? It's not saying that pink and green are equal. It's saying pink plus red equals green plus red equals pink plus red. So we're close, right? They're at least in the same room. We want to get these guys together. You know how it is at a party, right? You get these two people, you want to get them together, right? You got to get them in the same room first. Well, we got them in the same room. Now think about it. I don't know what any of these measures are, right? 90 degrees, 100 degrees, I don't know. But I do know red's the same as red, right? Always, every day. So some number plus red equals another number plus red. Think of a number in your head for red. How about 5? What plus 5 equals another number plus 5? What does that tell you about these two angles? They have to be, right? If I imagine 7 for green, I've got 7 plus 5, right? That's 12. So 12 equals what plus 5? Well, 7, right? If this is 7 plus 5, and that's also a 5, well then this must also be a 7, right? Because they're equal. Maybe you like PEMDAS better. Subtract the red angle from both sides, right? Anything minus itself is what? Anything minus itself is 0. So in other words, we have green plus nothing, after we do PEMDAS, equals pink plus nothing. In other words, the measure of the green angle equals the measure of the pink angle. In other words, they're congruent, right? I'm going to show you what we did here. We said, look, green and red have to add up to 180 because they're on a straight line. Red and pink also add up to 180 because they're a straight line. Well, if green and red makes 180 and pink and red makes 180, then green and pink must be the same. If you take a number and add a number to it and you get 180, and you take another number and add that number to it and you get 180, well then these have to be the same. 7 plus 5, if we made up 7 and 5, right, has to equal something in 5. 7 plus 5 equals something else plus 5. Well, the only thing it could be is 7, right? If you have 6, you get 7 plus 5 equals 6 plus 5. That doesn't make any sense. 7 plus 5 equals 10 plus 5. That doesn't make any sense. 7 plus 5 equals 7 plus 5. That's the only thing that makes sense. This common angle that they share in their equations kind of determines what else is going on. And that's what's happening, isn't it? This angle is shared between these two, right? Here's 180 degrees, right? And here's 180 degrees. They share this angle. If I change this angle, watch what happens to these guys. They change too, don't they? And they match. We've just represented it mathematically. So did we need this? No, we didn't need that. Did we need this? No, we didn't need that. But they were true. True but not useful in this case. If this equals 180, that equals 180, then they equal each other. Therefore, since these are the same, these must be the same as well. They gotta be. Now we proved what we call the vertical angles theorem. I don't like the name of it, and I'll explain why later. It's VAT, V-E-A-T, and it's a theorem because it's provable. We had to use angle addition postulate instead of segment addition postulate. You can put the pieces together, right? 2 pieces added up make 180, right? Something like that. You're allowed to do that. That's a postulate. But this is proven. This with math. So if you want to call it VAT, that's fine. Vertical angles theorem. Later, you'll be able to just see an X and go, okay, top and bottom are equal, sides are equal, blah, 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 blah. How would we prove? I just said sides are equal. Vertical angles means up and down, right? So it's saying the vertical angles are always the same. That's what this is saying. But what about the left and right side angles? The horizontal angles. Are they going to be the same as well? Conjecture, yes. How would we prove that? Perspective. Right? We're not changing the question. We're not changing what we're looking at. We're not changing what we're working on. We're just looking at it in a different way. Right? I'm not taking it apart and rearranging it. That wouldn't be allowed because that would change what I'm working with. Right? Maybe I screwed it up. Right? If I take this piece out here and switch it with that piece there, this might be impossible to solve. I don't know. But as long as I know it was once correct, I can get it back. Vertical angles are the same. Up and down. That's what this says. How would I prove it for these two? I just did it for the vertical, right? Green and red makes 180. Pink and red makes 180. Therefore, green and pink are the same. How would I do it for blue and red? Maybe you can't. She says they will be. That's her conjecture. What if I turn the paper? Vertical angle theorem says the vertical angles will be the same. What are our vertical angles now? Blue and red, right? It was a matter of perspective. I don't like vertical angles theorem because it makes it sound like only the vertical angles are the same. But in reality, vertical is in the eye of the beholder, right? Horizontal is just vertical sideways. How would we prove it? Well, don't blue and pink equal 180? Don't pink and red equal 180? Subtract the common angle. What's left over must be the same. It's the same proof. So we can say by similar logic, we know that blue and red are the same. Basically, it's just saying, hey, do the above, but with the other angles. Exact same thing. Ain't nobody got time for that. When you finish your proof, what I like to do, usually people write Q dot E dot E D dot, and it stands for like proof is in the pudding. It's like Latin or something. Another way they'll do it is they'll like box at the end, and I think it comes from like boxing your answer. It means the proof is finished. I like to do this. I call it swag box. 2 boxes. And the reason for that is because it's like a cube. It's like next level. I don't know. You can come up with your own way to end your proofs. I typically just do the 2 squares. We've done our first proof. How do we feel about this? There's no, here's how you do a proof. Everything you do is going to be your own way of seeing it. And as long as your logic's good and you come up with the answer, okay, sure, awesome. This is what real math is like. We've been showing you math for the longest time. Is here's the 5 steps, here's how you do it. And if you forget your steps, well, you're screwed. Because you have no idea what it means. When in reality, this is math. What you're doing before was calculation. which is a part of math, but not very interesting. I want you to write a post about this. Why are the top angles always the same? Can you show it? Can you explain why? How do you know the side angles are the same as well? Don't be afraid if you make mistakes, because again, that's what the comments are for. I can be like, hey, what about this? What about this? Can you change this? Right? Go and try it. Give it a shot. This is a mandatory post for next week, okay? Get started on that. Draw a diagram, make some pictures, label your angles. Show me why they have to be the same. Feel like you can attempt that? Doesn't have to be perfect. I just want to see it, then I give you comments, and we can work on it, okay? See you guys later. Take care. If you see Chase in the hallway, just go, angles! It'll scare him. He's terrified of them. He told me at the beginning of class, I don't like angles, Mr. Mack. I don't like it. I just don't. It's like, who hurt you, Chase? Who hurt you? Angles. Wash the desk and then go to the bathroom. Get a super soaker for all this stuff.
Well, I am never early. Something bad is happening today. What the fuck?
You know, there are some people in this school, and I have friends who, don't get me wrong, but oh my god, there are days when I'm just like, you, like, can you just stop reading?
I love you.
Like, I have a lot of those people.
Well, I'm not.
Like, I'm friends with some of them too.
Here's what's gonna happen today.
There's only like one person I really just don't like. Don't get me wrong, I'm friends with some people. Like, there's just some days when I'm like, oh my god, you're like, hell. Ew. Annoying me. Someone was typing too loud in world history.
Someone was typing too loud.
Yeah, and I was like, I was just getting annoyed.
Mr. Matt.
It's an even number. Oh, Cliff, sorry I missed that.
They were like banging on
What's up?
the keys.
I was early to class. This is not a good thing. Something bad will happen today, and I'm sorry if anything does.
Okay.
I don't like this.
Hopefully
I'm
I
never
did.
early.
Okay.
Anything.
I have a headache today.
Sorry, Demery.
But my cat cut me up last night.
Hi, Olivia. Yeah, let me know if you're here, guys. Hey, Maddie. The B-Day version of 4th hour feels to me like it's the B. It should go with the other half of 3rd hour. Like the vibe in here is the same as my 3rd hour. My 4th hour, I always think you guys are 3rd hour because of that. My 3rd hour is a very specific vibe and you guys vibe with it. 4th hour has a very specific vibe. I feel like they need to interchange you guys. You got some mail? Okay. Today's an exciting day. No peeking. I don't know about angles yet. And all right, I see Maddie, Olivia, Jordan, Isaiah, Logan, and Ann. I do not see Cooper yet, or Troy, or Zach Hall, or Jackson, or Mitchell, or Jaina. But it's early. It's early. Bell hasn't rung yet. Jamie's here. Gage, I don't see. CJ's here. Hey, Troy. Today's an exciting day. We're beginning geometry proper in the way that last time we did like postulates, which are like leaps of faith. Today we're actually proving something. Yeah. Oh, it's a very exciting step, especially since last year we didn't get to proving something until like quarter 2. What? I'm sorry, what did you say the bell rang? Oh, that's exciting.
Two people actually had a fight.
What?
I said it's the accuracy.
Not so good.
No.
All right, so I don't see Mitchell yet. I don't see Jackson yet. Can you send a message to Jackson? Or Zach or Cooper. Before we get started, I want to give a couple seconds to get you guys in class, because I've got some announcements to make having to do with portfolio reviews, just so everybody's clear on what's going on. So portfolio stuff. So next week, the plan is for, are you guys B-Day or A-Day? You guys are B-Day, right? So B-Day plan next week is you guys get to skip next week for portfolio reviews. A-Day people go next week. However, if you have not met with me yet, and there's some of you in here that have not, you need to meet with me before the end of this week, hopefully today after school between 1:05 and 3:25 on Meets. I'll send you an email.
I met with you, right?
Yeah, you're good. CJ, you hear me?
Yes.
And that you need to meet with me today. And then if you didn't meet with me last Wednesday like you're supposed to, even if you meet with me today, you will meet with me next Wednesday despite being a B-Day, okay? So everybody's meeting me next Wednesday except for B-Day people that already met with me. Does that make sense?
Yeah.
So A-Day people, you're going to do it for a grade. So people online, I'll see you next Wednesday for portfolio review. People in here, you won't unless you haven't met with me yet, okay? Or like in Lexi's case, Lexi met with me, but just not last Wednesday. She met with me a couple days ago. So you'll meet with me next week too, okay? Right, for a check-in. We talked about that. We can either do that, actually, we can either do that today or next Wednesday. It's up to you. Because we said Friday I'd check in again. Would you rather check in next Wednesday? I thought so.
Wednesday.
Yeah.
I thought this one or everyone.
Nah, no. So listen up. Next Wednesday, we're starting our alternating schedule. So A-Day or B-Day kids will go on every other Wednesday. The first Wednesday will go to A-Day. So they're all going to be there. So everybody online, you're going to show up next Wednesday online to do a portfolio conference. B-Day people, you don't have to, unless you screwed up the portfolio thing last Wednesday, like you didn't meet with me or met with me a little bit later than you were supposed to, okay? Or if we met and I was like, dude, we need to make sure you know what you're doing, you gotta meet with me again. So, so Lexi, you met with me a couple days ago, but we're still gonna need to meet next Wednesday to make sure you're good to go, okay? And that's fine, because it'll just bring up your grade. Not today. Oh, we can do today if you want. It's up to you. Because we've met. Okay, then next Wednesday?
Yeah.
All right, cool.
Okay, that'll work.
The reason I gotta not do like these makeups so much is because what happens is I spend all my time doing makeups and not online reading stuff and giving comments and feedback, right? So if you haven't met with me yet, you're gonna meet with me next Wednesday, even if you're a B-Day person, cool?
Is it Wednesday and not Thursday?
It's Wednesday. Well,
Okay.
the time slots are Tuesday, Wednesday, Thursday, but most of the time slots are Wednesday, right?
Okay, because Thursday I'm babysitting and the kids don't shut up.
Gotcha.
They scream.
Have you tried tape?
Taping them?
Punting works too.
Yes.
Rat poison. Not. Oh yeah, that always takes.
It takes a lot of rat poison. That's expensive. Duct tape is cheap.
I mean,
Where's packing tape?
your hands work just well.
All right.
Oh, is that a sleeper hold?
So we talked about portfolio reviews and how it's going to work. You should have links up if you've met with me of the video of us going over stuff. There are a few of you the video didn't work correctly and all I have is the audio. But in general, you should have that up there. I think there are also a few where I didn't hit record, like the first ones that I did. But in general, it should be up there. So if your parents have questions about that grade, they can go there and look at what we talked about. Also, it's good for you because then if I said, hey, fix this, and you're like, okay, a week from then, oh, I need to fix something. What was it? You can go back and watch. Questions on this. This is what we did yesterday. So people online obviously can't see your faces and read your minds through a computer. I'm not that good yet, but I'm getting there. In class, normally I would be able to. And we'd be able to have a conversation about it. How do we feel about what we did yesterday? I want to do a quick recap. Concepts. Segment addition postulate. Remember, postulates are leaps of faith. We can't prove them, but we know that it has to be true. Otherwise, we wouldn't be able to do anything in math. So we have to take a leap of faith. One of those leaps of faith is that if you have a long piece like this, and you break it up into its pieces, those pieces, when you add them together, will add back up to it. Right? Doesn't matter what order you put them in, it'll work. So for instance, this piece right here, EF, is made up of two pieces, AB and BC. And so before we didn't know what this was. So what we said was, well, whatever this is will be what happens when you take this guy and take this away, right? If you subtract this much from 10, what's left over will be AB. We digging that? So what we said was, well, how long will this be? It'll be whatever 10 minus 6x is. We're doing 10 chickens minus 6 ducks, right? We've got an x here and no x there. So we can't simplify that to like 4 or 4x. We just have to leave it as this. So this will be whatever this minus this is, so I called it that. It'll be whatever 10 minus 6x is. Cool. Same thing here. Since BC and CD are pieces of GJ, down here in the teal, the cyan, if you will, we know that since this is 6x and that's 14x, what's left over has to be ax, right? Then we added them all up and did this. We set up our equation. We found that x was 1. Trust me on that. Are we cool with that idea of matching things up and taking things apart? Okay. We feeling decent about that? Okay. Andrew? Right. So I want to move on. Yesterday, this was all based upon a postulate. Remember, a thing that we can't prove. This idea that you can break it up and put it back together, right? But we want to minimize the number of postulates, because if everything's a postulate, then you haven't really done anything except make a bunch of stuff up, right? So we minimize that as few as possible. One of them, segment addition postulate. And then the rest are theorems that we actually can prove, right? Either based on those postulates or other theorems. And today we're going to do our first proof, our first theorem. So today's pretty exciting. The first thing we're going to do is we're going to imagine. Okay, this is kind of difficult, but if you imagine with me, I know it'll be like it's real. Okay, it'll be real. What you imagine is, I want you to imagine an x, not your x. Okay, not your x. Get him out. Get him out. Get him out. Be gone. Be gone.
That's out of your head.
Okay. I'm talking about like the letter x. The letter X, okay? I know this class can bring up some trauma, spoiler warning, or not spoiler warning, but like trigger warning. We will be talking about X's in here a lot, okay? I'm sorry. We have to. It's like when you're afraid of snakes and they like throw you in a tank full of snakes to get over it, right? It's exposure therapy. It's gonna be just like that, okay? So, it's gonna be just like that. So imagine the letter X. Okay, and if you imagine it with me, it's kind of like a pair of scissors. Imagine, okay, forget X. Imagine a pair of scissors, okay? You have the one scissor and the other scissor and they intersect, right? Imagine that. Close your eyes. Imagine that with me. Imagine a pair of scissors. Maybe the handles are like black and the scissor, the cutty part is like just metal. You know, they're like old school. They're not safety scissors. Imagine. Try really hard. Imagine, do you see the scissors?
Yeah.
Do you see the scissors? Okay, great. Now the reason we're talking about scissors is because we really want to talk about X, right? But we can't talk about X, okay? So imagine the scissors. They have a scissor on the right and a scissor on the left, and they intersect at some point. Doesn't matter where. Now math is all about describing relationships. Sorry, we're going to talk about relationships in here. Notice that the scissors, as they move about that intersection point, they don't change size, but there is something different about scissors like this and scissors like this, right? Right? They're changing something else. What did you say, Demery? Width. Yeah, like the width between the pieces, right? Is what you're saying? Now, if these scissors that you're imagining are 100 feet tall, right? But they're still held the same way, like this, the relationship is the same, right? Even if they're 100 feet tall, the relationship between here and here is the same. It's not a measurement of how far they're apart, because that could be like, you know, half an inch. But 100 feet tall ones would be like, I don't know, 5 feet apart. We want something that's going to be the same here. So we need a new way to think about it. We can't just measure how much it is between here and here. We have this thing called angles, right? Heard about that? Right? Angles. We're going to talk about what that is today. Angles. Angles. Not angels, but angles. L before E. L before E. So we're going to talk about this, because if you notice, what do you notice? What do you notice about the scissors? As I open and close them, what do you see? Yeah, go ahead, CJ. The point stays still, the angles around it change. What else do you see? So the size of the angles change. Yep, that's what CJ was saying. What else do you notice about that? No, keep going. Keep going. What about the size? Lexi.
It's the same on both sides and the same on top.
All right, so Lexi says it's the same here and the same up top. So the vertical angles, the top and bottom ones are the same, and the horizontal angles are the same.
Don't hit your head.
Right?
Do not hit your head though.
All right? Be like Josh Morris. You hear about that?
Yes, because thumb.
Yeah, he was sharpening a knife the wrong way. You were there? Oh, wonderful. So you were the supervision, huh? Yeah, okay. I mean, it was his fault for making you supervisor. All right, so Lexi says that the sides will be the same angle and the top and bottom will be the same angle. Now, is that just because my scissors are connected here? If I connected them somewhere else, would that change? We'll find out. So again, we're talking about scissors because we're talking about X, right? We're not allowed to talk about X. So here's a random X. And Lexi's conjecture. A conjecture is something that she thinks is true that we haven't proven yet. So we're going to prove her conjecture. She says if we have an X, right? Let's call it two straight lines put together, right? That's what an X is. Do we agree by that? Okay. Let's call this line ABC. Jared. So imagine, or the word let is what I like to use. We're not talking about your X's.
I don't have any.
Whoever Henry is.
Yeah.
Whether future or current X. So we're going to let ABC be a line. That's what this means, right? Imagine a line. We'll call it ABC. Cool? Now imagine another line. Let's call it DBE.
I heard that one. I'm sure the microphone is.
Now, even if I don't draw this out, imagine a line ABC and imagine a line DBE. What do you notice about these two names? Yeah. They both have a what? There's a B? Yeah. So, and it's in the middle. In other words, that's where they intersect. Without even drawing it, you know the lines intersect at B, correct? Okay, awesome. So imagine two lines that intersect at B. Awesome. Where's B? I don't know. There's a B. This side looks longer than this side, but we didn't say anything about that. All right, it's just a drawing, right? SpongeBob quote. So we have only said we have an X. Doesn't matter if it's 6 inches on this side, 3 inches on that side. We haven't talked about that. Because if we were talking about a specific X, we'd have to specify, like, okay, let this be 6 inches, let that be 3. No. We're using a general X. Could be any X. Okay. Is this mic on?
That mic.
Yeah.
So Lexi, careful.
Yep.
Oranges.
Whoa.
Tangerine.
Not allowed. Hey. 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 There's some things we don't say in here.
I'm sorry.
I'll think about forgiving you.
Please do. I can't live with an adult being angry at me.
And Lexi's conjecture is this. What we're trying to prove is Lexi's conjecture. She says that the top angles and the bottom angles will be the same. So let's give them some names and some colors to make it a little bit easier. So the pink angle, she says, should be the same as this green angle. Let me zoom in a little bit. Now, pretend we didn't have colors, right? Pretend we didn't have colors. Let's give these angles some names. I'll still use the color just to make it easy. How do you tell someone which angle we're talking about? How are we going to name it? Yeah, go ahead.
Point A goes down to point B. Grab back up to point B.
Okay, so ABE, angle ABE. Could we have given it another name?
A.
Abe. Oh yeah, we could just call it Abe. Yeah, that's true. So we have angle Abe. Would EBA also work? EBA, yeah, it would work. What about BEA?
No.
No. Do you see how it kind of gives you this angle that we haven't drawn in yet? Right. So what we want to do is make sure that the vertex, the point where the two lines intersect, is always in the middle. Where's the B? It's in the middle, right? There's a B. It's in the middle. And we want to prove that the pink angle is the same as the green angle. What do we call the green angle?
CBD.
Nice. What's the other option?
BBC.
Would you rather call it DBC or CBD?
CBD.
I think that's a good choice. We did it, boys.
We've achieved.
And we want to prove that they're the same. Now, when we talk about numbers, numbers are equal. That's how you know they're the same, right? 5 equals 5, right? Numbers, amounts, quantities can be equal. However, ideas, angles, figures, these ideas, we can't say they're equal because they're not numbers. So we have to use a different symbol. It's kind of silly. It's an equal sign with a little tilde on top.
That's an estimate estimation, isn't it?
Ooh, when you use 2 of the squiggles, it means estimation.
Oh, okay.
When it's like this, it's just a different symbol. It looks similar, but it's different. We call this congruency. You might have heard of it. It means congruent. When ideas or figures are the same, we use the word congruent. When numbers are the same, like if I were to tell you that this is 90 degrees and that's 90 degrees, then we could say the measure with a little m here of this angle would equal, regular equal sign, the measure, right?
Okay.
It's kind of silly, right? Numbers can be equal, but ideas can't. I don't know. So we use congruency. We want to prove that these two angles are the same. In other words, that their measures are equal, right? That's what we want to prove. That's Lexi's conjecture. Top and bottom go together, right? She also said sides, but let's calm down, okay? We don't want to do that much work today. So, oh, we're proving vertical angles theorem today, Landry. Stick around. So Lexi's conjecture is that because of Scissor Theorem, which is what we're going to prove today, Scissor Theorem, otherwise known as vertical angles. I don't like vertical angles. I think Scissor Theorem is better, okay? Something, something, they're scissoring, so they're the same, right? So here we go. These two, hey, I had to bust this one out last year. Where is it? Where is it? Where's my saying? Your words, not mine. Okay?
Did you just say that?
Mm-hmm. I had to say that a bunch, because I think it was Alex Anderson was like, instead of calling it vertical angles, he wanted to call it Scissor Theorem, and he explained why, and I was like, your words, not mine, buddy. But hey, you do you. So we've got this angle here and this angle here that are the same. We're going to prove that that's true always. Okay? It's not just my scissors were special or that it hit at the right spot. Okay? It's not about location here. So here we go. Here we go. How are we going to prove this? Well, much like this problem that we did the other day, if we want to know what AD is, this whole length, there was a lot of other things we had to do first. Answering what AD is without knowing what these are right off the bat is a tough question. And so what we started doing is writing down relationships. Hey, I noticed that AC is the same thing as EF, right? I noticed that BD is the same thing as GJ. I know that these three pieces should make up KL. We just started writing that stuff down. So let's start writing down relationships. What do you notice about these angles? First of all, we have some other ones, right? Got a blue angle right here. We'll make the other one. What color do you want it to be? Purple. Purple? I like purple. 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 Purple.
You're like a...
Purple.
Yeah,
Purple. 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 Purple.
The cat does not match that color.
It's because of the way that this camera is different than this camera, and so they have different like color corrections. Yeah. I didn't get the new one for that yet. No, it's at home. It's actually a really, really old one.
Oh, see, that is if you want to show that board, you can change the camera angle to that one. Actually, if you want.
Oh no, is the thing not working?
You can choose that camera and dance.
Oh, but it's not working today for some reason. Sorry, I don't know what's going on. Yeah.
Or we were gonna say we were gonna do foot shots, so foot pics. Oh.
I need a camera under the desk. Yeah, foot cam. All right. If you subscribe, it's like 5 seconds of feet. Okay. That's right. Boys got to pay the bills. All right, so, hey, it's real work. All right, so, what do you notice about these angles? Now, some of you guys are going to be like, well, I know that the pink and the green are the same. Well, no, we don't. That's what we're trying to prove. Well, I know that the blue and the purple. No, we don't. We haven't proven that. Well, what do you notice about these angles? What relationship do you notice here? First of all, when we talk about angles, what are we talking about? What's your favorite angle? What's the one Grandpa SquarePants said, never chase after a bus? Huh? Remember rock bottom?
Oh, 90 degree.
90 degree, right? Never chase after a bus, especially one going up at a 90-degree angle, right? Oh, we will.
Can't wait.
Has dead pixels? No, it's the green screen just being crappy because there's light shining through the room. So we have 90-degree angle. Now, question, why do they call it 90 degrees? Wouldn't it be nicer to use like 100? Like, I know like 100 is bigger, but like what if they said 90 was 100? Like, if you have an L, it's 100 degrees. And then if you had two L's back to back, you'd have 200 degrees, right? Or maybe it's 50 and 50. I don't know. Why'd they choose 90? That seems like... It is 180 according to whoever said what degrees are. But what if we invented a new way to measure and said this is 50, that's 50, that's 50, that's 50, 200 all around?
That would be a lot easier. Wouldn't it all go to be...
It's going to be 360 all around. How do you know that?
90 times 4.
90 times 4, or you know 360 no scope, right?
Yeah.
Snoop Dogg, 420. right? MLG Pro. Right?
Yeah.
Okay. So all the way around is 360.
Suddenly 2012 Xbox.
Yeah, exactly. 2012 Xbox. You get the like 5-year-old on there.
You can hear his parents right in the background.
Yeah. Anyway, so we got 360 all around, 90 times 4. You can also do 100 plus 100 plus 100 plus 100, but we overshot by 10 each time, right? Minus 40, right? So 400 minus 10, 10, 10, 10, right? I don't know, different ways of thinking about it. So why do they use 360 as their number? Well, this is kind of similar to why we use 12 on a clock. Does anybody know why we use 12 instead of like, what if we had like, I don't know, 20 hours in a day? It'd be the same amount of time, but the hours would just be bigger, right? Why do we use 12 and 24? Well, here's the thing. Our system, this system here, which is not American, by the way, you could just be like, oh, why not? That's true, but you have to convince the rest of the world to operate on it, otherwise it's not very useful, right? It's almost like time zones, right? Which are awful.
They were made up by train companies.
I know, right? But they convinced everybody to do them, and so now we're here, right? But you have to have a pretty good reason to convince people. Otherwise, they're not going to get on board. No pun intended. And then it's going to be useful, right? Because if you're like, oh, it's 8 o'clock, and someone's like, no, it's 10:30, and you're like, well, not by my clock, because I use a different system. You're like, okay, good for you. No one's going to care and have any idea what you're talking about, right? So you have fun. Why do they use 12? Anybody have an idea? Oh, gotcha. Okay, well, that's not what I heard, but maybe you're right. What I heard was that 12 is really divisible. If we use 10, for instance, what numbers divide 10? Now, ignore 1, ignore 10, because every number is divisible by 1 in itself, right? Yeah, 2 ways to divide 10, right? How many ways can you divide 12? 2, 3, 4, 6, double, right? Twice as many. And could we use a bigger number that's more divisible? Sure, but then we have lots of hours. Like, calm down, right? We want a small number. We like small numbers. So 12 is the biggest number for a while that has 4 divisors. So it's highly divisible. That's useful because if you want to say, look, half the day goes by, a quarter of the day goes by, eighth of the day goes by, you can do that. An eighth of a day is 3 hours because 24, right? What's an eighth of a day if it was 20 hours long? Not as nice. You get a fraction. We try to avoid fractions. So they use 12, highly divisible. Same reason they use 360. If we use 50, 50, 50, 50, we get 200 all the way around, but 200 is not a highly divisible number. 360, we can divide it by 2, we can divide it by 3, we can divide it by 4, we can divide it by 5, we can divide it by 6, we can divide it by 8, we can divide it by 9, we can divide it by 10, we can divide it by 12. Very divisible. So when you want to do a quarter of a turn, no big deal, 45 degrees. A quarter of a turn for 200 around would be 50, not too bad. Eighth of a turn would be 25. A 16th, oh, 12.5, right? You see how we quickly end up getting into decimals and fractions? 360, eighth of a turn, no big deal. What's an eighth of a turn for 360? A quarter of a turn's 90. So what's eighth of a turn? 45. Right? What's a third of a turn for 360? A full turn's 360. What's a third of a turn? 120, right? You can do a sixth, 60, right? You can do a 12th, 30. Highly divisible. You can even do a tenth of a turn, 36. So that's why they use 360. So all the way around is 360. Question. What's halfway around? What's halfway around then? And then 3/4 of the way, that's going to be 180 plus 90 again, right? 270, right? Couldn't you do 100 plus 100 plus 100 and subtract 30? Right? So 270. Awesome. 180 halfway. What do you notice? Boom. Right? Has to. That's our definition of an angle, right? Or 360 degrees. It's all the way around the circle. See how this makes a circle? So we're going to start writing stuff down. Write that down, write that down, write that down. And we don't know if it's going to be helpful or not, but we do know it's true. This is going to happen a lot, okay? You're teaching kindergarten, and you're asking a question, right? It has nothing to do with geography. And this kid raises their hand, and you call on them, and they say, Texas is the biggest state in America. And you're like, I'm teaching math, sir? right? Sir, this is a Wendy's, right?
Wendy's
What they're saying is true, it just might not be helpful. That's going to happen a lot in here, okay? You're going to say lots of things that are true, it just may not end up being helpful. We'll write it down, though. So you said that the pink angle, which is ABE, I'm not going to write the letters because it just saves time to use color, plus the purple angle, plus the green angle, plus the blue angle is going to equal what? 360, no scope. So we know that this has to be true because it's all the way around the circle. What else do you know? That's what we're going to prove. Yep, that's true. That's true, but we haven't proven it yet. We're trying to get there. Once we've proven it, then you can be like, oh yeah, this theorem says it's true. Move on. But for now, we're going to prove it. What else do you notice? So all of them together equal 360. What else do you notice? What do you see?
Not much. Anything but.
Everybody else is looking at their calculator, so.
What am I supposed to do?
Well, we don't know. That's the problem. Unlike regular math class, where it's like, here's 5 steps, and as long as you remember to do them and don't screw them up, you're fine. Proofs don't have it that way, because it depends on how you look at it. There's lots of ways to do it. And as long as you're being logical and everything you've said has been true, and it leads you to a conclusion, then you're fine.
I mean, angles that are the purple and blue angles should be the other one.
Ooh, okay, that's what it looks like. Again, this is a generic x, so we don't know that for sure, right? It could be any x. We didn't specify that. All we know is that this is a straight line, ABE, ABC. And we also know that DBE is a straight line, right? That's what we said. 2 straight lines that intersect. That's all we're looking at here.
I'm sorry for yawning.
No, it's okay. Andrew, you have something to say?
ABE and CBD are the same angle.
ABE and CBD are the same?
Yeah, if they're the same, aren't ABD and EB?
That's a really good conjecture, and we're going to have to look into that. We don't know that. The first thing you said if this, right? Which we haven't proven yet. But you're right. If this is true, maybe that means these are also the same. That's what we're going to look at next. This guy's 10 steps ahead of the game. What else do you notice? Again, all we know is that this is a straight line, and we know that this is a straight line. That's going to be helpful. What do you see? Again, we're just writing down relationships. What do you know about straight lines? They don't curve. What do you know about angles? Sure. All the way around is 360. A quarter of the way around is 90. What else do you know?
I really am trying.
No, it's okay. I know you're trying. You don't need to feel bad. We're just giving you time to think. This is fine. I know normal math class, this means like, oh my god, the teacher's mad and they need an answer. No, I'm just giving you time to think. And different ways to think about it. If I hold this one steady, right, and just move this guy, what do you notice? Sure, it changes. What else do you notice? Yeah, this point stays fixed. That's true. What else you got? Keep going. Again, a lot of things we're going to be saying that are true but might not be helpful, but that's okay. Keep going. What do you mean? What was that last part? I couldn't hear. So like from here and here, they're connected, and as I pull it apart, it makes an angle. Is that what you're saying? Okay. And what angle is this? It goes from 0 to what? If I could go all the way. 180. It goes half the circle, doesn't it? Okay.
Oh, wait.
What do you have to say?
Is the two straight lines all both supposed to be 180?
So a straight line is 180 degrees.
Yeah.
So what does that tell you about pink and purple?
Add to 180.
Do you know what they are individually? No, it could be like 30 and 150. It could be 90 and 90. I have no freaking clue, but I do know that they add up to 180. They have to, right? That's a straight line. So let's write that down. So pink and purple make 180. So Gage, what we're trying to do is that Lexi said when you open the scissors up, the top and the bottom angle and the side angles are always the same. So we're trying to prove that that's true, that the top and the bottom will always be the same. So I drew a generic pair of scissors, 2 lines, right? Both intersect at B. And we're proving that this is true. The top and the bottom angle are the same. So far we said all the angles have to add up to 360. That's valid. And then we just figured out that these two make a line, right? So that means this adds up to 180. What else do you notice?
Green and blue also.
Green and blue add up to 180? What else do you notice? Again, we're going to have a lot of things that are true but maybe not are helpful, so don't be afraid to just say stuff that's true.
Green will always be a bigger angle than blue.
Remember, this is a generic X. I drew a picture to make it easier for you to see, but we don't know, like, what kind of X. All we said is 2 lines intersecting, right? What else do you see? So we can't say it's for sure bigger. Pink, purple, and green are 270. Oh, is that because you're thinking they're all 90? Okay, so all I said was generic X. A specific X would be everything's 90. I'm saying just any X, okay? It's okay, you're tuning in just now. All we know is that we have 2 lines and they intersect at B. Tell me something about them. How they intersect? I don't know. Is this 3 and that's 6 for like length? I don't know, man. Right? It's just a generic X. That's going to be something we got to get used to for geometry, right? It's generic. You guys are used to everything being very specific. We want to keep it generic because we want to prove this, that it works for any X, not just, you know, an X that has, you know, this long here and this short here and they intersect. You know, we don't want to do that. That's not very interesting. For any X, oh, that's interesting, right? What else do you see? Pink and purple add up to 180. Green and blue add up to 180. What else? Blue and pink are 180. Don't they make a line? Okay. Blue and pink, 180. And green and purple. And that covers all our combos, right?
Oh, wait. We're supposed to be in that this whole time?
Oh, you're cool. That's cool. Purple and green, is that what you said? Purple and green? Okay. Now, which angles do we care about, by the way? Which ones are we trying to prove? Yeah, AB and CBD, right? Nice. So we care about green and pink. We've got a lot of things here with green and pink. Isn't it true that if something equals something, let me say this. If this equals 180 and this equals 180, don't these two equal each other? Here and here?
Yeah. Don't they all equal each other?
They would all equal each other. Now, why did I choose those two? Notice that they both share purple and they both have the colors we're looking for. So in other words, instead of writing purple and pink make 180, I can write purple and pink equals what?
Green.
Green and purple. Are you smelling what I'm stepping in here?
Kind of. Is it like, what's that property?
We'll have to talk about it another time. We're so close to proving that purple and green are the same. If you want to get started on a post about this, talking about how you knew they were 180, etc., I'll write some comments. It doesn't have to be done or perfect. Just give it a shot, okay?
Yeah, but there's a property that's like that. I don't remember what that property is called.
I don't know, man. Hey, Eads, you just get back from WAC?
Yeah.
Yeah? Are you guys like showing up in the middle of 4th hour, or what's going on there?
Yeah.
How does that work?
Early in like last 10 minutes to show up.
Gotcha, okay.
Until next week, that might be the last 20.
And then you won't be able to use that as an excuse anymore, huh? What's your 4th hour class?
B.
Oh, so not a huge deal?
No.
Gotcha.
All we do is walk the track. Not fun.
Nah.
Hard on that.
Sebastian's in early.
Oh, he is? No way.
First time ever.
Alright, I gotta get this out of here. Today's an exciting day in geometry. We did our first proof.
What are we going to be doing today?
Ooh, I love how you're interested already.
I'm excited for today.
How about relationships? You know, that's what we do. How about our exes?
Yep.
How things relate. It's real emotional in here sometimes. Especially since most of you guys were abused by your ex, and when you learned about it in middle school. Math torture, math abuse. That word right themselves. Pardon me. My exes live in Texas. What's up, Sebastian?
Today?
There we go. Gage, present. Gina showed up. Mitchell showed up. Jackson, not sure if he did. Looks like Jackson did not. We got everybody else, it looks like. Wait, Cooper? Wonder if Cooper emailed me. No email from Cooper. Okay. My cameras are screwed up today. I can't switch over to the dance cam. Kids last hour were like, we need a feet cam. Underneath the desk. Everybody subscribes. Get 5 seconds of feet cam. No Cooper as far as I can tell. Alrighty. Yeah, let me know if you're here. We got Mac. Leah, I think, is at home. And I need Haley, Jordan, and Kaylee, but Sebastian's here already. Okay. I'm getting tired of seeing this one. Oh, maybe I got an email. Felt something. Nah? Okay. Oh, hey, Jordan. Amazing. It's like a kangaroo. I'm Australian, mate. All right, Leah's here. Hi, Leah. Got Jordan. I don't know. I hope not. Yeah, McDonald's are here. We just don't have Haley and Kaylee yet. I know, none of that. All right. All right, so you're tired of seeing this guy, I'm sure. Before we get going, I just want to make an announcement that next week, make an announcement. Mind your business, David.
Word of the week. What kind word intrigues someone's entire day? Have a great day.
All right, my own announcements. Next week, 8A people are going to meet with me for portfolio conferences. So that's the people at home right now. Yep, on Wednesday. I don't think we'll need Tuesday or Thursday, but I'll leave slots open as well, like I did last time. But it'll probably just be Wednesday. That's only half the kids. If you did not meet with me last Wednesday, last week at your assigned time, right? So if you met with me this week, this still applies to you. So Camden, right? I will need to see you next Wednesday, even if you're not 8A people. Cool? And that's just to check in, make sure things are going well and all that stuff. I just want to make sure you're on. A lot of people that didn't see me, that's because they didn't really know what they were doing, what was going on. And so meeting more at the beginning is going to be better. Eventually, I do want to switch over to where we do all kids on one day. But for now, I'm spending like 20 minutes getting kids set up when they don't know what they're doing. And that's fine. That's fine. I want to make sure everybody's kosher and feels like confident in what they're doing. And also, more grades, if we have to think about them, is better because if you screw up one, right, you know what I mean? So I think you guys would probably appreciate meeting every week, even though it sounds like more work. Really, it's not. It's the same amount of work. You just either meet once or you meet twice, right? Now, then you got to, if you meet once every 2 weeks, then you're showing me a lot of work all at once, right? That's all it is. So I don't know. We'll talk about it. But yeah, if you're an 8A person, next Wednesday will be your conferences. B-Day people, only if you didn't meet with me on time, do you need to meet with me next week. And then B-Day people will be the week after that. And we'll see how long that alternating schedule has to go on. Next week we have regular school time, more or less, right? We only get out like 30 minutes early, I think.
Yeah.
I'm not sure how that works exactly, but I'll take a look at it. But yeah, that's the deal. I see everybody here except for Kaylee, I think. As of right now, Kaylee might have just emailed me. I felt the buzz in my pocket. No, it was Cooper. I think it's Cooper's Wi-Fi must be acting up because he just sent me 2 emails back to back saying the exact same thing. Right, anyway. Oh, Kaylee's here. Awesome. Okay. So yeah, 8A people meet next Wednesday. B-Day people will not unless you didn't meet with me like you're supposed to. I will be available, fingers crossed, after school today from 1:05 to 3:25 for anybody that needs portfolio conference stuff. I've been hit and miss on that, especially with you. But we got stuff done. Cam, did we get stuff done or did we not? Not yet? Okay. Yesterday I was supposed to be available, but my computer stopped working at like 1. And I had to like turn it off, like force shut it down. And when it finally turned back on, it's like updating. Right? So I had to wait another 2 hours for that to happen. Windows is doing stupid stuff right now. Normally I don't have any problem with this system. The system's old. I built it back in like 2013, but it's still a pretty good computer. It's not as good as my home one, but it's pretty good. So hopefully Windows will stop being dumb and then we'll be good to go. I will be available today from 1:05 to 3:25. Please meet with me, so if we can do that, that'd be great. Again, I know I've been running you around because my computer's been stupid. Hopefully, fingers crossed, today will be fine. If not, we'll see you next Wednesday. We'll get it squared away, okay? But that's the idea. So today, this guy right here, we've seen this a lot, right? Y equals x plus 5. We thoroughly understand it by now, right? We got 2 numbers. We can rewrite it like this. Clearly showing that what we're talking about is all the numbers separated by 5, right? Yeah. Okay, awesome. Lots of different ways to write it, but that's one way. Which number is going to be bigger, the x or the y? X is always going to be bigger? I ask the questions. Y is bigger. Why? How do you know? Anything plus 5, right, is going to be bigger than the thing you started with, right? If you take any number and add 5 to it, it's going to get bigger, right? So y will be bigger, always. Even if it's written like this. It's the same idea, just written a different way, right? The distance is 5. A number plus 5 is the other number, right? They're always separated by 5. So when someone asks you, what's the solution to this equation? Right, normally when we ask for a solution, it's like 2 plus 2, what's the solution? 4. Well, isn't 3 plus 1 also a solution? Right? Now, typically when we say solution, we mean the simplest solution. 4 is simpler than 3 plus 1, right? Solution. Things that make it true. What's the solution to y equals x plus 5? Strange question, isn't it? Right? Why is that strange? If I say what's the solution to 2 plus 2, it's not that strange. Why is this strange? Camden?
Because you can put any.
I know what you're saying, but I'm going to do this thing that I do a lot of the time. So I could put like 5 here and 12 there.
Well, I mean on the y minus.
This one? 5 here and 12 there?
Or
I know what you mean, but I'm being that guy.
spaced apart by 5.
They have to be spaced apart by 5. So any pair of numbers you can put in, as long as they're spaced apart by 5, right? That's what you're trying to say, right? There's lots of possible solutions. Does that mean any numbers work? No, but infinitely many do at the same time, right? Infinitely many do, but you can also get wrong ones, right? So it has to be numbers like 0 and 5, 1 and that's a big comma, 6 and 2 and 7, etc., right? Those will all work. You dig, right? 7 minus 2 is 5, 2 plus 5 is 7, right? No big deal. So that's what you meant. So when we say what's the solution, there are infinitely many solutions. Not all work, but there are infinitely many of them. It's not like 2 plus 2, 4, right? Sure, 3 plus 1, but like, come on, right? Come on. It's the same idea. Yeah.
How come there's many solutions, but all the numbers you got don't work? Right there.
So there are infinite combos, right? 0, 5, 1, 6, 2, 7, 3, 8. I can go on and on forever, right?
That's why they call it count.
But some combos, not on this list, right? But combos outside of this list don't work. Like 0, 6. So it's kind of weird, right? Some infinities are bigger than others, right? All the combos in the world, any possible combo, like you were saying initially kind of, right, with your wording, like any possible combo, that's one infinity. That's really big. But if it's only a certain kind of combo, even though there's infinitely many of them, that's kind of like a smaller infinity.
Yeah.
Isn't that weird? There's both infinite. There's no such thing as infinity plus 1, by the way. Doesn't work. It's just infinity. But some are bigger than others. So it's like we said, it's an infinite dartboard, and you throw a dart, and you can still miss. You can still miss, right? If I put a dartboard with all the possible combos on there, there's still going to be combos that don't work.
Then you throw out like 13.
Right, you see what I'm saying? That would be a miss, even though there's infinitely other ones to hit, right? That's really bizarre. Infinity is weird, guys. It's weird. It makes math strange, but it comes up really fast, right? It's not, you don't have to get to calculus before you start talking about infinity. It pops up pretty quick. Yeah, infinite solutions that are spaced apart by 5. Yep. So when we ask you something like this, and they say solution, what do you respond with? Yeah. 4. So 4 plus 1 is 5. And you said 1?
Yep.
What about 1? You said 1? 1 plus 1 is? So 1 doesn't work. What do you mean by 1? Four worked, right?
Yeah.
Did you say 4 and 1 because you saw the 1?
Yeah.
Yeah, sorry, that happens. Misspeaking happens. So 4 is the only solution. One solution. That's it. X can only be 4. Here, X could be any of these, right, on this list.
Yeah.
How do I know what the rest of the list is? Well, I can follow a clear pattern. It goes up by 1 both sides, right? Oh, all right. So there are infinitely many solutions. So when we graph it, what we're showing is all the solutions that work, right? We have this coordinate plane, right? This thing right here. And this represents all the possible combos.
Well, the reason why for X comes because you put 5.
It locks it in, right?
Yeah.
It's asking a different question. Only one variable. When we have 2 variables, but only one equation, infinitely many solutions. If we have 1 variable and 1 equation, oh, no big deal. It's always one solution, right? Good observation. So here is a visual representation of all the possible combos, right? Every combo shows up here. Not just the ones that are separated by 5, but all the combos. Name 2 numbers, it's on here, right? the line y equals x plus 5, 1, 2, 3, 4, 5, and each x goes up by 1 as y goes up by 1, right? If you go down, they both go down, something like that. This line represents all the combos that work for this particular thing, right? That's what that represents. So that's what we've been talking about. Do you have something to say? Wait, you had something to say?
Oh, no, I don't.
Oh, okay, cool. But you're good with this? Awesome. So that's what that is, right? Again, infinite combinations here. There's infinite combinations on this line. But which infinity is bigger? All of this, right? Cool, cool, cool. All right. The difference between this and this we talked about as being numbers separated by 5, numbers separated by 6, right? They're going to have different solutions, right? A different list, so they're going to have a different line. But they're kind of similar, right? Because the numbers that go up or that are different by 5 can be this. Combos are 1 and 5, or 0 and 5, 1 and 6, 2 and 7, 3 and 8. But the combos for going apart by 6 are 0 and 6, 1 and 7, 2 and 8, etc., right? Slope. We did kind of talk about that a little bit, right? The idea is that both go up by 1, right? As x goes up by 1, the y goes up by 1. As x goes up by 1, the y goes up by 1. The difference is where they start, yeah? Here, we start on 6, whereas here we start on 5. So what these represent is, in another way, is starting on 5 and 0. 0 is kind of always where we start for x, right? Starting on 0 and 5, go up by 1 every time. Starting on 0 and 6, go up by 1 every time. Slightly different, but very similar, right? Then we talked about this. Starting on 0, go up by double every time, right? Whatever this is, it's double. Or in other words, go up by
Or even the other way around.
2 every time. That's another way to look at it. While this goes up by 1.
Or if you flip the question around, it's same thing.
Division, right, yeah, exactly. It's the other way. Look at this guy and it'll tell you what you get over here, right? Take this and divide it by 2 and you get what's over here. Yeah?
You could do the same thing if you add like 1 or 2 or 3.
What?
Start from the 5, 1, 2.
Another way to write this is this. Starting on 0 and 0, right? We always start on 0 for x. Start on 0 here, right? We started on 5 and 6 earlier. Starting on 0 and 0, x is going to go up once because x always goes up by 1, right? We always have that just to, you know. But y is going to be twice as big, right? Which number's bigger, the x or the y here?
X, Y.
Oh, we have differing opinions.
No, it would be Y.
Why,
Y.
I ask the questions.
Y.
Why?
Because that's what you're checking.
Why is y bigger than x here, always? How do you know?
It's the solution.
Yeah? Go ahead.
Because Y is 2 times bigger than X.
Isn't it weird that this looks kind of like x is twice as big as y? That's what you want to say. But be honest, you did, right? And you actually did out loud. But it's actually the other way around. What is y? Y is twice as big as x. That's how we read that. So y is bigger.
Like that.
Because that's what this says. Y is twice as big as x. And if we check it, it always is, right? If x is 1, then y is 2. If x is 2, then y is 4. Y will always be twice as big. Now, sometimes they're tied, right? Because twice as big, 0 is 0, right? Now, this number here represents the relationship between how much we go here and how much we go here. It's 2 versus 1. In other words, 2 over 1. In other words, 2. Right? The relationship is 2 for y, 1 for x. That's how we're going up. More simply, 2. Here, there's a 1 in front of there, right? Have you guys heard about that? Right? You guys have heard about that before. And it's because we're going up by 1 for both. In other words, 1 for the y, 1 for the x. 1 over 1 is 1. 1x is just x. Save ink. So this number in front is the relationship between x and y, and this number here is kind of where we're starting, right? So without plugging in numbers, and again, could you be plugging in numbers in your head and I don't know? Sure. But let's do honor system here. Without plugging in numbers, what pattern are we going to get out of this? First of all, where does the pattern start? Yep, 0, 3. And how does the pattern go up? Well, x always goes up by 1, right? Yeah?
Then, y goes up by 2.
By 2. So we have 5 or 6 here.
5.
Let's check that. When we plug in 0, do we get 3? 0 for x, do we get 3 for y? 2 times 0. Add 3, 3. Yep, checks out. Good. So we started off in the right spot. That's good. What about 1 and 5? We plug in 1, do we get 5? 2 times 1 plus 3. Yep. Do we plug in 2, we get 7? What about when we plug in 3, we get 9? 6 plus 3, right? Yep. Checks out. Oh, did I screw that up? Is that what you've been focusing on?
Yeah.
8 and 3 makes 11. Normally, I would have turned that into an accidentally on purpose mistake. We would have gotten there, and you've been like, yeah. Oh, what? And I've been like, gotcha, but you caught me ahead of time. I wasn't smooth. You got your hand raised, bud? Or are you stretching? Oh, sorry. My wrists are always really awful because I drum so much, and I didn't take care of myself. Same thing with my ears. Didn't wear ear protection. So, like, gripping things now, ugh. I grip too tight when you're playing. You're supposed to be, like, super loose. Helps you go faster. But the problem is when you go faster, you want to, like, tense up, right?
Yeah.
Ends up screwing up your hands. Gotta pull on my thumb and like yank it out. Awful. You ever do that? Like have to pull like a joint out or something? I gotta do that all the time. Not even hurting right now, but it's making me feel like I'm hurting just thinking about it. Okay, so that's all this represents. It's a pattern, a relationship. As we go up by 1 for x, we go up 2 for y. That's what this is. If I were to change this to a 3, how would that change our numbers?
Go up by 3. Go up by 3.
So will we still start in the same spot?
Yes. Yeah.
So now what would this be?
6.
15, thank you. Math is hard.
Okay, you can say.
Say again? Camden, did you say something?
What?
Did you say something? Oh, it's like ventriloquism in here.
Did say something. But then it seems like you're actually like that much.
What do you mean?
Like you do 3 times 1, you get 3. 3 times 2, you get 6. 3 times you get 9. 3 times 4 is 12.
Why do you think that is? 3 times 1 gets 3, but we have a 0 getting 3.
Yeah.
3 times 2 gets 6, but we have a 1 getting 6. Why do you think that is? Yeah?
Where we start.
There's already a 3 that we start with. Another way to think of that is, look, if I do 2 times 3, that's 2 groups of 3. But don't I already have an extra group of 3 to begin with?
Yeah.
So it was really 3 times 3. If I start on 5 times 3, well, it's really 6 times 3 because I have an extra group of 3, right? That's all. It's coincidence. But yeah, it starts on 3, and so there we go. Okay. Now, I always start the class with a review-ish type of thing, you know, easy into it. It's like a jacuzzi, you know what I mean? You don't want to jump in. You get burnt. You gotta ease yourself in. Where are your gods now? What does this mean? Take a guess. Where are we starting the pattern? Let's check that. If I plug in 0, do I get 3? 0 times anything is 0.
No, you don't.
Hold on. 0 times anything is 0. Add 3, we get 3. We're Gucci. We're Gucci. Now, normally, x goes up by 1, right? What are we going to get here? Make a prediction. We're supposed to go up by how much each time? 2/3, it says. So we can do mixed number 1 and 2/3, right? Let's check that. If I plug in 1, do I get 1 and 2/3? What'd I goof? Yeah.
Got to add 3.
It should be 3 2/3, right? 3 2/3. This should be the answer. Now the question is, I'm supposed to go up by 2/3 every time. Oh, that checks out. Right?
Yeah.
That checks out. We did it right. We just added it to 1 for some reason. I don't know why. Something I said. So the next number would be, after you add 2/3, what? 4 1/3, because we have 3 4/3. Right? So it should be 4 1/3. You're like, this is gross, right? Next is going to be what?
5. Just 5.
Right, straight up 5. And if you look, 3, plug it in. What's 3 times 2/3? Couple ways to think of it. Think of fractions just as like a unit, right? We've got 2 chickens, and we're timesing it by 3. 2 chickens times 3 is how many chickens?
6.
6 chickens, right? So we have 6 chickens, or 6/3. 6/3 simplifies to what? 2. Plus 3 is? Another way to think of it is, if I have 2/3 times 3, we can do 3 times 3, or 3 times 3 and divides by 3 is just 1, right? 3 divided by 3 is 1, and then times it by 2, we get 2. Then add 3, you get 5. So you can either times by the top and do 3 times 2 first, and then divide by 3, or you can divide by the bottom first. 3 divided by 3 is 1, times by the top 2. I'm gonna spell that out, just in case. Couple ways to do 2/3 times 3. Sometimes it's easier one way, sometimes it's easier the other. So I'm going to show you both, okay? We can either divide by the bottom first, because division, right? That's what that is. 3 divided by 3 is 1. And then we're supposed to times by the top. So the answer is 2. Another way is we could do times by the top first. 3 times 2 is? And then we have to divide by the bottom, right? Divide by 3, and we get 2. You can do multiplication or division in any order, doesn't matter. Just know that the bottom means divide, top means multiply. Your call what you want to do. What? Top first? Yeah, most people do. Sometimes it can be really useful to not do the top first, like this. 2/3 times 27. Would you want to do this and get 54 and then divide by 3? I have to think for a second if 54 is divisible by 3. 9 times 2 is? That's nice, right? 27 divided by 3 is 9. Times 2, 18. Sometimes it can be really useful to divide first, because division makes smaller numbers, right? And we like small numbers. Okay, cool. So this is still kind of nasty. What if there's another way to think of this? Oh man, I had an idea. What I really wanted to do was this. There we go. See how I did that? Covered it up with the paper. Genius. Saving trees, baby. This is where we start, yeah? What if we didn't go up by 1 every time for x? Did you notice that after we went up by 3, we got a nice number? Let's go up by 3. And when we go up by 3, we know 3 divided by 3 is 1. Times 2 is 2. We get 5 for an answer, right? That's what we got last time. Will my next answer be a nice number?
Yes.
If I add 2/3, what do I get? I get 5 2/3. You liar. That's not a nice number, unless you're weird.
4.
Sticking my tongue out, you just can't see it. Is that a nice number? No, not as nice as this anyway. Will my next number be a nice number?
No.
What's it gonna be?
It's going to be 5 and
6 1/3, there you go.
it's good. And the next one will be 6.
Next one's gonna be nice though, right? Straight up 7. You notice a pattern?
Yeah.
We start on a nice number. 2 more go by, and then the third one's nice. 2 more go by, and then the third one's nice. So what if we just went up by 3s instead? It'd be a lot easier to write. So if this is 3, now we go up to 6. 6, we said got a 7, right?
Okay, it was 8.
What pattern do you see so far? As I go up by 3 here, what happens to the y?
Goes up by 2.
Goes up by 2. So by prediction, what should our next nice set be? It should be 9 and... Ooh. Let's try that out. Does that work? You want to times by the top or divide by the bottom? We're doing 9, right? 9 divided by 3 is? Times 2 is? Plus 3 is? 9! Checks out. Now, what if there was an easier way to figure out how to get nice numbers? Because again, you're going to get them eventually. It's the same thing. We're just ignoring the dumb numbers, and the reason we want to do that is because we want to graph it. Right? How many lines do you need to make a point? Or how many points do you need to make a line? Well, 1 point, what's my line? I don't know. Is it going this way, that way, that way? I don't know. What about 2 points? Only 1 line, right? That can go through those 2 points. So I don't care what my points are. Right? They're all going to be on that line anyway, right? That line represents all the possible versions, right? All the possible combos. I'm going to get those for free anyway. How about we graph the nice ones? Those are easy. Now, if only there's a way to know where you're going to get nice ones. You could think like, oh yeah, 2/3, you do it a bunch of times, every 3 times it's going to be nice. Ladies and gentlemen, what does this number tell us? Yeah. Remember, this is the starting spot. What does this tell us? Yeah. X will eventually get bigger. What do you mean by that?
No, Y will eventually get bigger.
Well, they all get bigger, right? Yeah. As X gets bigger, Y gets bigger. If X gets smaller, Y also gets smaller, right? Right? If I start out with 10 for X, that's going to make a big Y. If I get smaller for X, Y will get smaller too, right? They move together. We call that relationship a direct relationship. As one goes up, so does the other, right? Maybe they're not even, but they move together, right? Yeah.
X will eventually catch up.
You think so?
Yeah.
When will X be bigger than Y?
X1 to 12. And
They're together here.
yeah.
Do you see how X is eventually going to get bigger?
Yeah.
That's wild. That's because when we times by 2/3, we're taking whatever X is, we're only taking a piece of it, right?
Yeah.
So eventually that piece of X will be smaller, which is what Y is made out of. And X will originally be bigger than what Y is because you're only taking a little bit. Words were hard there. If you didn't understand what I said there, don't worry about it. Yeah, X will eventually be bigger than Y because Y is going to be whatever 2/3 of X is. That's already smaller, right? 2/3 of X is smaller than all of X, right? And then if you add 3, for a while, you know, this will be bigger. But eventually, 2/3 of X is going to be so small, 3 is not going to make up for it. Next step, if we go by 3 again, we get this, right? In fact, anything higher than that will be smaller because they're already tied, right? So this number tells us the relationship between X and Y, doesn't it? You notice anything about these numbers and these numbers? Kind of far away. Let me zoom in. Sorry for the pen, guys. I need to use markers. If you want to use nice numbers, you'll use these numbers. X goes up by 3, and the Y goes up by 2. X goes up by 3, and the Y goes up by 2. You could add 2/3 every time. Or you could say X goes up by 3, Y goes up by 2. That's when it'll be nice. X goes up by 3, Y goes up. Rise over run. Dude, that's the slope. Go up 2 over 3. Go Y plus 2. Go X plus 3. You'll find another nice point. Right? You remember that from graphing last year? It'll always find you another point. And a nice one, if you start out nice. So we could think about this a lot to graph it and think about, okay, we're starting on 3 and 0, right? And then we're adding 2/3 every time and we can just put dots in, right? But some of our dots are going to be messy, right? Some of our points. Or you can think about what your teachers have been telling you before, now that you know what it means, right? And you can kind of use a shortcut. You notice a pattern, right? We're going to start on 3, and then if we go up 2 and over 3 every time, plus 2 to the Y, plus 3 to the X, we're going to get another nice point, right? And that's how we can graph. So for this one, you could do this. We're starting here on 3, right? 0 and 3 is where we start our pattern. And then I could go over 1 and then up 2/3, so I'm like here, right? You dig? Or, since my slope is 2/3, that relationship is 2 for the y, 3 for the x, right? I can go up 2 for the y and go over 3 for the x. Now notice if I had gone 2/3, I would have been there, right? 2/3 more gets me 1/3. You see how it would have been there anyway? Camden, you smell when I'm stepping in?
Yeah.
I'm going fast. I'm using an awful lot of words. You doing okay? I know you're trying to stretch and stuff. You able to be here? If you can't, that's fine. I just want to make sure you're here. And are we feeling all right?
Yeah.
It's kind of like, let's see if I can get it to work. No, it's cool. No, you're good. But how do you feel about this so far? You feeling okay? For real? Okay, because sometimes I say stuff, I'm like, dude, I'm out in like outer space here. But I don't know. You guys seem to be all right. If you're not, let me know. You know. That's what it means, guys. You can graph any line. Even when it looks like this, instead of looks like this, you could graph it when it looks like this, I bet. Right? That's a bit harder. That's a bit harder. The distance between y and 3 times whatever x is 1. So all the numbers that are separated by that, you could just put dots down, right? Plug numbers in, see what happens, right? Another way is you could rewrite it to look like that. And now you know, x is going to go up by 1, but y is going to go up by 3, right? Starting on 1. Starting on 1. X goes up by 1, y gets 3 times bigger, right? So x is 1, y is 3 times bigger. We're going to be like here. Get out of here. Write me something. I'm going to get to posts. I know I haven't gotten to comments in a while. It's because I'm trying to get all these other kids caught up. I'm spending all my time doing portfolio reviews when I should have done them last week, right? Had them all done last week at least. I want to shrink that down so I can spend more time focusing on reading portfolios. Hopefully with kids getting their stuff together, that'll be fine. I'll see you guys later. Take care. Have a good weekend. Nice job, boys. Hey. Hey. Spraying down these desks. Los Angeles. Everybody that walks in. Like a theme park, if I put like a sign up that says, beyond this point you might get wet. It's fair. Why is it when I don't plan my lessons, because I have like a headache the night before or something, and I'm like, okay, I'll just figure it out when I get there. Lessons are always better. Frustrating.